In this video, I will go over every single point that you need to know because you may encounter in paper one for AQA A Level chemistry. In this video, I will focus on the exam rather than focus on every single point of the specification for paper one. So if you want to have a quick revision of every single topic before your exam, this is the video for you. So let's start with the first topic, which is model of the atom. And the model of the atom may come in the exam from year to year. It's not in every single exam. What you need to know about this is the comparison between the three models, the Plum-Pudding model for J.J. Thomson, Rutherford, the nuclear model for Rutherford, and the Bohr model for the electron shell model. So Plum-Pudding model, J.J. Thomson discovered the electrons, and he described the atom as positively charged balls with negative electrons embedded in it. Rutherford later on discovered the nucleus and that the nucleus has a positive charge. When he did his experiment with the foil, gold foil, he discovered that the mass of the atom is centered at the center, and that the nucleus is positively charged, and the electrons just surround the positively charged nucleus. He didn't speak about energy levels. Bohr is the one who discovered the energy level with his model, which is the electron shell model. So he described the electrons as existing in shells or orbitals of a fixed energy, and that when the electrons move between the shells, an electromagnetic radiation is emitted or absorbed. Later, he discovered that not all the electrons within the same shell have the same energy. This is why he discovered as well the subshells, as we know now as the S, P, D, and F. Sometimes in the exam, they may ask you to write the electronic configuration of a certain element or for an ion. You don't need to even look at the atomic number. You just need to locate its position in the periodic table and use the periodic table to write the electronic configuration. So the first two blocks here are the S block. And this one on the right here, these six from 3 to 0, these are the P blocks, which means the outer shell electrons in the P suborbital, and the S means the outer shell electron in the S suborbital. And then the one in the middle here, these are the D blocks, or as we call them, the transition metals. So when you try to write the electronic configuration, you just need to locate where is the atom. For example, if I'm going to attempt the zinc here, we can see that the 1s is completely full, and then we have the 2s, the 2p, then the 3s, 3p, then the 4s, which is filled before the 3d. Remember that 3d has higher energy than the 4s, so that 4s is filled first. And then for zinc, it will be 4s2, and then at the end, it will be the 3d10. So this is how we write it rather than trying to do the calculations. The electronic configuration, there are some exceptions with this rule I was talking about. Because we have copper and chromium, there are some exceptions for filling the subshells where there is stability associated with a half-filled or fully filled subshell, especially when we're talking about the d orbital. So an electron shifts from the 4s into the 3d subshell to achieve this stability. So we have for copper, the expected electronic configuration would be R1 and then 4s2 and then 3d9. So we said that the 4s will be filled before the 3d because the 3d has higher energy or the 4s has lower energy. But actually what happens is that one electron moves from the 4s into the 3d because now we achieve a full sub orbital or a full d subshell. So this gives more stability to the copper. So when they ask you about the electronic configuration of the copper, you have to put it as 4s1 3d10. Also, chromium is the same situation, but now we will move the electron from the 4s to the 3d to achieve a half full d suborbital. So the expected one for chromium is 4s2 and 3d4. So, but the actual one is 4s1 and 5d and 3d5. So there are filled the of the d subshell. This is why it's more stable. When we talk about the cations or the ions, when we lose electrons, sometimes as well, they ask you to write the electronic configuration of an ion. When we are dealing with the transition metals, where the outer shell electrons are in the d sub orbital, then we need to take note that although the 4s or the s orbital is filled before the d orbital, but they lose the electron first as well. Meaning that for transition metal, for example, if we talk about copper as we've seen it, so for the ion from copper, it will lose the electron from the 4s before it starts losing the electron from the 3d. So this is only exception for the transition metals because the 4s will lose the electrons first, even though it has lower energy. Moving on to the ionization energy. What you need to know about the ionization energy. So most of the talk about ionization energy in the question comes in the form of describing the trend in the ionization energy. Sometimes as well, they may ask you to write the equation for the first or second or multiple ionization energy for a particular element. So remember that the first ionization energy is the energy needed to remove one electron from each atom in 1 mole of gaseous atoms, if they ask you for the definition, to give 1 mole of gaseous 1 plus ion. So when you write the equation, the thing that you need to take note of is that you need to add the gas symbol for both the atom and the ion, and you need to add the electron as well. Refer to only 1 mole of the substance when you do this as well. So successive ionization energy, the second, third, or whatever. Remember when you write the equation, for example, if we write the equation for the second ionization energy of sodium, we start with the sodium ion. We don't start with the sodium metal. And then again, we put it in the gaseous state, and then that will give us sodium 2 plus. This is the second ionization energy, also as gas, and the electron. Different factors affecting the ionization energy, because they may ask you about the trend in the ionization energy, why it increases or decreases across a period or along the group. So there are three factors that affect the ionization energy: the nuclear charge, distance from nucleus, and shielding. Nuclear charge means that the nucleus has more protons. So as the atomic number increases, the number of protons increases, and the attraction between the outer shell electrons and the positively charged nucleus will be more, meaning the outer shell electrons will need more energy to be removed. So the ionization energy will increase across a period when because there is an increase in the nuclear charge. And then we have the distance from the nucleus. As you go down a group, you're going to see that the distance from the nucleus increases. This is because there are more electron shells now. So even though the positive, the nuclear charge increases, but the outer shell electrons become further away from the nucleus. So as the distance from the nucleus increases, the outer shell electrons will be less attracted to the nucleus, and less energy will be needed to remove the electrons. And then shielding. So we can see the shielding in the also in the along the groups. So as you go down the group, there will be more inner electron shells, and these inner electron shells will act as a shield. So they shield the outer shell electrons from the effect of the positive nucleus. So as you go down the group, the ionization energy decreases, and this is because there are more shielding. So these inner shells, electron shells, will shield the outer shell electrons, so they are from the nucleus, so they are easier to remove. Electronic shell structure and ionization energy. So you can see that when we talk about the successive ionization energy for a certain atom or a certain element, you can see that the successive ionization energy increases. This is because you keep removing an electron from an increasingly positively charged ion. Also, there will be an jump in the ionization energy between shells. So as you go down, or as you go through the successive ionization energy, when you jump from one shell to another, there will be a jump in the ionization energy as well, because now we are removing electrons from a shell that is closer to the nucleus. Trends in the first ionization energy, we said we have all the three factors, the nuclear charge, distance from nucleus, and shielding. So we talked about the ionization energy down the group. So we have group 2 elements or alkaline earth elements. One of the trends is the decrease in the ionization energy down the group. This is because of the increase in the shielding and the distance from the nucleus. And then the across the period, so the period will across the same period, you will have the same number of shells, electron shells. So the shielding and the distance from the nucleus is not doesn't don't make massive impact here. The main impact will be the nuclear charge. As you go across the period, the nuclear charge increases, so the outer shell electrons will be more attracted to the nucleus, so will need higher ionization energy to remove or higher energy to remove. However, across the period, we have two exceptions. The two exceptions are the drop that you can see between group 2 and group 3. This drop is because in group 3, you start to remove electrons from the p subshell. So now the p subshell is further away from the nucleus and a little bit more shielded than the s. So when we are talking about period 3, though we are talking about 3s and 3p. So this is why aluminum will have the first ionization energy will be lower than magnesium. And we have another drop here between group 5 and 6. And the reason behind that is due to electron repulsion. So we have the phosphorus and sulfur. Phosphorus is group 5. They both have the same shielding, but phosphorus is group 5, where the electron that is removed from a singly occupied orbital. But when we talk about the sulfur, the electron is removed from an orbital that has two electrons. So there is some repulsion between these two electrons, which lowers the ionization energy needed to remove that electron. This is why there is a small drop here. Some of these definitions may come in your exams, so make sure that you know these definitions about the atomic mass, because we are going to talk about the mass spectrometry. And mass spectrometry is one of the typical questions in paper one. So sometimes in the question about the mass spectrometry, they ask you to define a relative atomic mass or relative formula mass. Remember that when you define the relative atomic mass or relative formula mass, you will always refer to the scale where an atom of carbon-12 is 12. So relative atomic mass is the average mass of an atom of an element on a scale where an atom of carbon-12 is 12. And when we talk about the relative molecular mass or relative formula mass, it will be the average masses of all of the atom in the formula on a scale where an atom of carbon-12 is 12. So the mass of carbon-12 has a scale of 12. Now moving on to talk about the mass spectrometry or the mass spectrometer, where it's kind of a typical question in paper one. The mass spectrometer or mass spectrometry has four different stages. The most important stage that we would need to talk about, which comes in the exam, are the ionization stage and also the detection at the end. So we have four stages. We have the ionization, detection, ion drift, and acceleration, drift, and detection. So, first of all, the different particles, whether they are atoms or molecules, get ionized in the first stage. They form positively charged ions, and then they get accelerated, and they all have the same kinetic energy. So, we know that the kinetic energy will equal half mv squared, where m is the mass of the particle, and v squared is the speed squared. So, because they all have the same kinetic energy, the ones which have lower mass will have higher speed. So this is why the atoms or the particles with the lower mass will reach the detector first, because they're going to have a higher speed. So let's start to talk about the two different types of ionization based on what you need for the exam. So we have two types, the electrospray ionization and electron impact. Electrospray ionization, when you dissolve your sample and then you push it through a nozzle at high pressure, and then you apply a high voltage. It's very important to refer to the high application of the high voltage. What happens when you apply the high voltage? Each particle will gain a proton or hydrogen ion. Now the ions or the ionized particles will have hydrogen plus. So if you have something like M, it will be M hydrogen plus, not M plus. And then the sample will turn into a gas made up of positive ions. So these positive ion will have hydrogen plus or will have a proton. The electron impact, on the other hand, the sample is going to be vaporized first, and then an electron gun will be used to fire high energy electrons at the different particles. This will knock one of the electrons off each particle. So the particles will lose one electron and they will gain a positive charge now. The second stage is the acceleration, where they are accelerated and they all have the same kinetic energy. They don't usually ask about that in the exam. The ion drift, as I mentioned before, it's because they have all have the same kinetic energy. The one with the lower mass will reach the detector first. And then the detection, what you need to know about the detection. So the ions are going to hit the detector, and each ion will gain an electron, generating a current, and the abundance of each particle is proportional to the size of the current. This is how we find the abundance of the different particles or different ions in the mass spectrometer. So the mass spectrum that is generated will give you the mass over charge. The charge is usually, most of the time, is +1. So mass over charge is basically the mass of the particle. The particle could be an atom and it could be a compound as well, and or could be a molecule. And then on the y-axis, we have the relative abundance. And then in case of electron impact, the ions that we detect, the m over z, will be the mass of that particular ion. But if we use the electrospray, the m over z will be the mass +1 because we added a hydrogen ion now. This is very important when we calculate the mass of the particles, or when we calculate the relative atomic mass or the mass of the isotope when they ask us to do this, or the mass of the particle. So this is a typical question again in the question. This is a question where they give you the equation for the kinetic energy. And then they either give you the distance traveled and the time took by a particular particle, and then they ask you to calculate the mass of that particular particle. So how to answer these type of question? Remember that the mass that you use in the equation is in kilogram. It's not in gram. So if you're going to find the mass, remember that the value you're going to get is in kilogram. The speed, which is the v, it's in meter over second. Sometimes they give you the distance in centimeters, so you have to change that into a meter. And then when you calculate the value of the m, it's going to be in kilogram. You have to change this into a gram first by dividing by 1,000. So when you divide the kilogram by 1,000, that you're going to give you the mass in gram. This is the mass of one particle. Then they give you the Avogadro constant. So now you need to calculate the mass of 1 mole of that substance. The mass of 1 mole is basically the mass of the particle, whether it's an atomic mass or molecular mass. So the mass of one particle, multiply the mass of one particle by the Avogadro constant, that will give you the AR or the MR. So depending on whether it's actually an atom or is it a compound. Remember, if we use the electrospray, then the MR, the AR that you get, or the MR that you get, is actually not the MR or the AR, it's the AR +1. So to find the mass of that particular particle, you have to take away 1 because we added a proton. So the mass we calculated at the end is m plus 1, not the m plus. So this is very important. One of the typical questions as well that they ask you to give the equation, including the state sample for the formation of this ion strontium plus from strontium atom by shapes of molecules. Is one of the typical questions in paper one as well, but they can come embedded within other questions, not like a big question in A-level paper one. So in a shape of molecules, the thing that you need to know about is that the shape will depend on the number of bonds and the number of lone pairs of electrons around the central atom. So the remember that the shape of the molecule is governed by these two factors: number of bonds, number of lone pair of electrons. The idea is that the pairs of electrons are trying to stay at further apart from each other in space. So they will keep away from each other and take that shape. And then when we have lone pair of electrons, the repulsive power between the lone pair will be more than the repulsion between the lone pair of electrons and the bonded pair, which is more than the repulsion between the bonded pair and bonded pair. This is according to the valence shell electron pair repulsion theory. So the shapes of molecules, you need to memorize these ones. Okay, so these ones, because you're gonna identify based on the shape they're gonna give you, you're going to calculate the number of bonded pairs, number of lone pairs, and then you need to say what is the shape, what is the bond angle. So if you have two bonds with no lone pair of electrons, the shape is going to be linear and the angle is 180. And if you have three bonds and there is no lone pair, the shape is trigonal planar and the bond is 120. If you have four pairs, if we have four pairs, and these are as four bonds and no lone pair, it's going to be tetrahedral with a bond angle of 109.5. But if you have four pairs, but three of these are bonds and one is a lone pair, then it's going to be trigonal pyramidal, and the bond angle is 107. If you have two bonds and two lone pairs. Again, in total, there are four pairs of electrons, but two bonds and two lone pairs. The shape is called bend, or you can say V shape. The bond angle here is 104.5. Notice the difference in the bond angle between the three. The bond angle keeps decreasing as we go to the right as the number of lone pairs increases. This is because what we said about the repulsion between the lone pair is higher than the repulsion between the lone pair bonded pair, which is more than the bonded pair. So the bonded pair become closer to each other. This is why the bond angle decreases. Then if we have five pairs, there are four different situations. The first one, you could have four bonds and no lone pair. The shape will be trigonal bipyramidal, and this is going to be two bond angles. One of them is 90, the other one is 120. And then you could have three bonds and two lone pairs. The shape is going to be T-shaped, and the bond angle is around 88. You could say 90, they would accept it as well. And then you could have four bonds and one lone pair. This is called seesaw, and the bond angle, we have two different bond angles here. We have 87 and have 102. The fourth case for the five, if we have five pairs, is that you have two bonded pairs and three lone pairs. This is very common in the exam. So this is the central atom. There are two bonded pairs and we have three lone pairs. Then the shape is going to be again linear with a bond angle of 180. And then finally, if we have six, so we could have six bonds and no lone pair. It's going to be octahedral and the bond angle is 90. And we could have four bonds and two lone pairs. It's going to be square planar and the bond angle is going to be 90. How to predict the shape of the molecule? To predict the shape of molecule or determine the shape of molecule, you need to follow the following step. First of all, you need to determine or to find the central atom, and then you need to find how many bonds are there. So if we have something like hydrogen sulfide here, H2S, the central atom here is sulfur, all right? Because this is the atom where all the bonds are around, and we have two bonds around it. So first thing, let's look at the central atom. The central atom has six outer shell electrons because sulfur is in group self. So now the number of electrons in the outer shell is six. And then there are two bonds because there are two hydrogens. So we're going to add to the six two, which comes from the two hydrogens that make the two bonds. So in total, around the sulfur, there will be 8 electrons. Now we need to look at how many of these are going to be bonded pairs, how many are going to be lone pairs. So 8 electrons means there will be, we divide this by 2, there are 4 pairs of electrons. Okay, two of these will be bonded pairs because we have two bonds, and that means the other two will be lone pairs. So we calculate the bonded pairs, and the remaining will be lone pairs. So when we have two bonds and two lone pairs, the shape is going to be bent like water. So H2S is similar to water with a bond angle around 104. Irreversible reactions and equilibrium constant is one of these topics which can feature in both paper one and paper two. Paper one is mainly about equilibrium constants, which is the calculation of Kc. For paper two, it's more about the gas equilibria. So you have a reversible reaction, a gaseous reaction, and then they want you to calculate the Kp for this gaseous reaction. Kp can be calculated using this equation, which is the partial pressure, the product of the partial pressure of the products, each raised to the power of their number of moles, divided by the product of the partial pressure of the reactants, each raised to the power of its number of moles. So it's exactly the same like Kc, but instead of using concentrations, we are using partial pressure. How to calculate or to find the partial pressure of each of the gases in the reaction? We would need to use the mole fraction of gases at equilibrium. So the mole fraction of a gas is the number of the moles of the gas at equilibrium divided by the total number of moles of the gas in the mixture at equilibrium. Remember that we are talking about equilibrium at equilibrium. And then the partial pressure of any gas will equal its mole fraction times the total pressure. Usually in the question, they will provide you with the total pressure of the reaction. So what are the different factors that can affect the value of the Kp? The temperature will affect the value of Kp. This is because the temperature can shift the equilibrium towards the one of the reactions, one of the sides, depending on which side is exothermic and which one is endothermic. So if you increase the temperature, the equilibrium will be pushed to the side that has the side which is endothermic to oppose the effect of the increase in the temperature. That means that the partial pressures of the that side, which has now the equilibrium shifted to, will increase compared to the other side. So this is why the Kp value will change. However, the pressure does not affect the Kp value. So remember, if you increase the pressure or decrease the pressure, if the question comes that they used a smaller vessel, so there's an increase in the pressure, that will not affect the value of the Kp. And also remember the different factors affecting the decision of the equilibrium, because they are very common in paper one as much as they are common in paper two. So these are temperature, as we said, which direction of the reaction is going to be the exothermic and which one is endothermic, and the pressure in case of gases only. And of course, this for paper two, it's always going to be gaseous reactions. So the pressure, if you increase the pressure, the position of the equilibrium will be shifted to the side with the lower number of moles and vice versa. And finally, the use of catalyst. The catalyst does not affect the position of equilibrium, but it only affect the rate of the reaction, both the forward and reverse reaction, leading to reaching the equilibrium faster, because it actually increases the rate of both reactions at the exact same rate. So we just reach the equilibrium faster, but it doesn't affect the position of the equilibrium. So these are the type of questions that you may encounter in your exam, which are kind of typical questions. So you are provided usually with a gaseous reaction, reversible reaction, and they give you the delta H of that reaction to know whether the forward reaction is endothermic or exothermic. They will give you the number of moles of the reactants, one of the reactants at the beginning of the reaction. So this is 0.317 moles of the reactant, and they give you as well the number of moles of one of the products and want you to calculate the mole fractions. So remember, you're going to use the number of moles of the product to calculate the number of the moles of the reactant at equilibrium. For example, here oxygen, it's 0.12 moles, and we have 2 moles of nitrogen oxides give you 1 mole of oxygen, meaning the moles of nitrogen oxide that reacted was double this amount, so 0.24 moles. Now, the moles of the nitrogen oxide remaining at equilibrium will be the total, which is 0.31 0.17 minus the amount that reacted, which is 0.24. So this is how you calculate the moles of each at equilibrium. And then the other product here, the nitrogen oxide, this is going to be double the moles of the oxygen at equilibrium, because 2 moles of nitrogen oxide are produced when 1 mole of oxygen is produced. So it's going to be 0.24 moles. Now you can calculate the mole fraction of each. For example, for oxygen, it's going to be the number of moles, which is 0.12, divided by the total moles at equilibrium. So you're going to add the moles of oxygen plus the moles of nitrogen oxide plus the moles of nitrogen dioxide, which is the reactant at equilibrium. Then they usually give you the pressure of the system or of the reaction, or what is the pressure. So you can calculate the partial pressure of each and use the equation to calculate the Kp. And also the one of the common questions related to this is that when they compress the system into a smaller volume, that means we increased the pressure. And they ask you to deduce the effect, if any, of this change on the equilibrium yield of oxygen and on the value of Kp. We agreed that changing the pressure will not affect the Kp, so there will be no effect on the Kp. However, that will affect the yield of oxygen here, because in this case, when you increase the pressure, the equilibrium will be shifted to the side with the lower number of moles, meaning it will be shifted to the left. And that means that the yield of oxygen will decrease if we increase the pressure. There are 2 moles on the left-hand side, 3 moles in total on the right-hand side. And then finally, they can ask you about the temperature, the effect of temperature on equilibrium. So at the equilibrium mixture, allowed to reach equilibrium at lower temperature. Explain why this the yield of the oxygen decreases in this case. If we decrease the temperature, that means the reaction or the equilibrium will be shifted towards the exothermic side, and the oxygen is produced in the endothermic side. So thermodynamics is one of the main questions in paper 1, and usually it comes in the form of the Born-Haber cycle. Before I start talking about the Born-Haber cycle, we need to go quickly over Hess's cycle, which is mainly in paper 2, but we're going to apply the principles of the Hess's law into the Born-Haber cycle. So what is Hess's law? Hess's law states that the total enthalpy change for a reaction is the same no matter the route taken. So if you have one route like reactant react to give you certain products, whether it goes directly from reactant into product or whether it goes through an intermediate where reactant gives you an intermediate and then the intermediate goes to give you a product, for each of these reaction there will be a certain enthalpy change. Now we have 2 different routes. The total of route 1 will equal the total of route 2. Route 1 will be the one in one direction, as we see from the arrows. This is the orange one. Route 2 will be the 2 steps which are in the opposite direction, which go together in opposite direction to route 1. So they go in the same direction. So the total of the enthalpy change of route 1 will equal the total of the enthalpy change of route 2. If we have any of these missing, we can rearrange our equation to find the missing enthalpy change. So the types of enthalpy change, there are several types of enthalpy change. I will be focusing now on one of the important ones, which is the standard enthalpy of formation. Standard enthalpy of formation is the enthalpy change when 1 mole of a compound is formed from its elements in their standard states under standard conditions. So formation can be for organic, for covalent compounds or for ionic compounds. And it's from the elements and their standard states under standard conditions. So for carbon, for example, it's always going to be solid, hydrogen, gas, oxygen, gas. How to build Hess cycle and how to build Born-Haber cycle. So we're going to build Born-Haber cycle using the same principle for Hess cycle. Quickly, how to do this using the enthalpy of formation. So if we have a reaction like this one, we have sulfur dioxide hydrogen sulfide reacting together to give you sulfur and water. We have the enthalpy change for this reaction. We don't know what is the enthalpy change. We are not given the bond enthalpies for the different bonds of reactants and products. So we need to calculate the enthalpy change of this reaction using Hess's cycle. And we're going to do this using the enthalpy of formation. So we have first one the formation of the reactants from their elements, and the second one will be the enthalpy of formation of the products from their elements, which is basically the same elements. And now we have two routes, as we can see, based on the direction of arrows, and you can see that from the colors. So route one will be the two reactions, which are in red, which go in one direction. The route two will be the one in blue, which goes in the opposite direction. Route one will give you the enthalpy of formation of sulfur dioxide and two times the enthalpy of formation of hydrogen sulfide because we have two moles. And route two, in addition, of course, to the enthalpy of the reaction, which is missing. Route two will be three times the enthalpy of formation of water, and this is an element, it has zero enthalpy of formation. Root 1 equals root 2. When you put all the values that you are going to be provided with in the exam, there will be only one value missing, and you can find this value. Now, Born-Haber cycle, we're going to do the exact same thing. We are going to construct what is the Born-Haber cycle, applying the same principles for the Hess's cycle. So what is Born-Haber cycle and what's the purpose for this one? So Born-Haber cycle is basically for the ionic compounds. So we are trying to calculate or determine the what is called the enthalpy of lattice formation, and these are for ionic compound. Why are we determining this or calculating that? We want to compare between the values we are going to get from the Born-Haber cycle and the value from the data book or the theoretical value. Theoretical values assume that all ionic compounds are pure ionic compounds. So there is something called the pure ionic model assumption. Ionic model assumption assumes that all ions are spherical and their charge are evenly distributed around them. However, ionic compounds are, the majority of them are not purely ionic, but they have some covalent character. So when you compare between the value you get from the Born-Haber cycle and the theoretical value, and then you can find that these two are different, then that means that the compound is not purely ionic, but it has some covalent character. If they are very close to each other, that means it's more like a pure ionic compound. Now, when we construct the Born-Haber cycle, there are certain enthalpies that we need to account for and we need to use. The first one is enthalpy of formation, which we talked about already. And then we have the atomization enthalpy. So when you have the elements, you need to atomize the elements, basically converting them into gaseous state, and they have to be one atom. So this is the enthalpy change when one mole of gaseous atoms is formed from elements in its standard state. So if it's solid in its standard state, we have to convert it to a gas. If it's a molecule, we have to convert it into individual atoms. And then we have the ionization enthalpy, which is ionization energy, basically. So it's the enthalpy change when one mole of electron is removed from one mole of gaseous atoms to form one mole of gaseous positive ions. So this is the ionization energy we talked about. We could use first and second, third, even ionization energy. We could use just the first one when we construct the Born-Haber cycle based on the ions we have. And then we have the electron affinity. Electron affinity is the same like the ionization enthalpy, but it's for gaining electrons to form gaseous -1 ions. So this is the enthalpy change when one mole of electron is added, this time not removed, to one mole of gaseous atoms to form one mole of gaseous negative ion. Remember that the first electron affinity is usually exothermic because the energy is released when when an electron is added. And then the second electron affinity, when you add a second electron, will be endothermic. This is because you are adding electron to an already negative ion. So we would need more energy to add the electron. And then finally, the lattice enthalpy. So the lattice enthalpy of the standard lattice enthalpy of formation or of dissociation. These are opposite to each other and they have the same value, but one is exothermic and the other one is endothermic. So lattice enthalpy of formation is the enthalpy change when 1 mole of ionic solid is formed from its gaseous ion. So this is different from formation because formation is the one that we form the compound from its element in their standard form. Here we are forming the ionic compound from its gaseous ions. It's going to be exothermic deformation because it involves a formation of a strong electrostatic attraction between the ions. However, if we are talking about the lattice enthalpy, the enthalpy of lattice dissociation, which is going to be the opposite one, then we are actually making the ions, the gaseous ions, from the solid. So it's going to be endothermic. It's just the same, but it's in the opposite direction. So it's the same enthalpy change, but it's going to be endothermic rather than exothermic. You need to be careful in the exam which one they want you to calculate. Now the Born-Haber cycle diagram. So I'm going to show you a quick diagram for one of the ionic compound, and then we're going to do it. I'm going to do it with you step by step because in the exam there will be some steps missing, and they want you to do the calculation. So this is the Born-Haber cycle diagram for magnesium chloride as ionic compound. So how would we construct that? What are all of these arrows? So let's start. So we're going to start at the bottom with the magnesium chloride. Don't forget the state sample, which is solid. And then we will start with the enthalpy of formation. Enthalpy of formation is the formation of the compounds from its element and their standard form. So we have magnesium, which is a solid, plus the two of the chlorine, so chlorine, which is gaseous in a standard form. And then the next step will be we need to do atomization. And atomization, we're going to do it step by step. So we're going to do atomization for the metal and then atomization for the non-metal. It doesn't matter which one comes first, and you can start with the non-metal. So I'm going to start with the metal first. So the atomization of the metal. So notice that now the arrow goes in the opposite direction, and then that will give us the magnesium as a gas, plus chlorine is staying the same as it is because I haven't done atomization for chlorine yet. So this is the enthalpy of the atomization of magnesium. The next step will be the atomization of the chlorine, and now we have the magnesium is still a gas. And then I'm going to convert the chlorine into atoms. So there will be two chlorine atom and both are gas. And now it's the atomization of chlorine, but it's going to be 2 times the atomization of chlorine because we have 2 moles of chlorine atoms formed. Following that, we need to start to ionize these atoms. So I'm going to start with the metal first. So we have magnesium. So I'm going to give the first ionization energy of magnesium. So here the ionization energy, first ionization energy for magnesium, and that will give us magnesium, which is a gas, as plus. The chlorine will stay as it is, as atoms, gas, and don't forget the electrons. And then we're going to move on to the second ionization energy for magnesium because magnesium has to be Mg2 plus, so that will give you Mg2 plus and it's gaseous plus D2. Remember that we haven't done anything with the chlorine yet. 2 atoms of chlorine plus 2 electrons now. And now we need to start working on the chlorine. So we have ionized the magnesium completely. So now moving on to the chlorine, now we need to give the electron affinity for the chlorine to give the chloride. We have 2 moles of the chlorine, so it's going to be 2 times the electron affinity of chlorine, and that will give us the magnesium will stay as it is as gas 2 plus, and the chlorine will change into 2 chloride as gases. Now we added 2 electrons, so we remove the electron from the equation. And now finally we have now the ions of both elements in their gaseous state. So with this is gonna give us, now we're gonna make the lattice formation. So this is the enthalpy of the lattice formation. It's this in this direction. So if you have the enthalpy of lattice formation missing in your question, now you need to construct the Hess cycle, or you need to do the equation or find your roots. So the first root will be only the enthalpy of formation, because this is the only one that goes in this direction. All the other arrows go in one direction, as you can see this way. So they are in the opposite direction. So now this is the only one that has opposite direction. So this is going to be, this is the enthalpy of formation. So this is going to be root 1. All the other ones, we're going to add them together, will be root 2. And then we will rearrange our equation to find the another important thermodynamic concept that we need to calculate, and very common in the exam, is the enthalpy of a solution. So what's enthalpy of solution? Enthalpy of solution is the enthalpy change when 1 mole of an ionic substance dissolves in water to form an aqueous solution, in which ions are separated and they are surrounded by water molecule, meaning it's hydrated. So when you dissolve a solid, an ionic compound, into water, there is some enthalpy change. The sample for it is the delta H solvent solution, sol, and the units is, as usual, kilojoule per mole. For example, if you have sodium chloride as a solid, that will give you sodium ion aqueous plus chloride ion aqueous. Is it exothermic or is it endothermic? It can be either. So it can be exothermic, which means the enthalpy of solution is going to be negative, meaning that more energy will be released when the ions are hydrated than the energy that is required to break the lattice. Or it could be endothermic, meaning that the more energy will be required to break the lattice than the energy that is released when they are hydrated. So the process of hydration itself is an exothermic process, and the process of breaking the lattice is an endothermic process. So whether a substance dissolve easily in water or not will depend not only on the enthalpy of a solution, but also on the entropy, which we are going to talk about next. So the key concepts for the enthalpy of solution, we have a certain enthalpies that we need to use to construct the Hess cycle for the enthalpy of solution. These are the lattice enthalpy, which we talked about in the Born-Haber cycle, or which we calculated using the Born-Haber cycle. So the lattice enthalpy here is the energy required, but here we are talking about the not the lattice formation, but the lattice dissociation. So the energy required to break apart the ionic lattice into gaseous ions. So this is the opposite of the lattice formation, and it's going to be endothermic. So we would need to supply energy to break the lattice bonds and to form the gaseous ions. So sodium chloride solid will give you sodium ion gas and chloride ion gas. And then we have the enthalpy of hydration. And enthalpy of hydration is the enthalpy change when 1 mole of these gaseous ions, which we just formed, dissolve in water to form hydrated gaseous ions. These hydrated gaseous ions are the ones that are going to be formed when we do the solution of the solid. So this is also this is always exothermic, because water molecules form ion dipole interaction with the ions. So for example, we have a sodium ion gas will give you sodium ion aqueous. So this is the enthalpy of hydration, which is exothermic, and chloride ion gas will give you chloride ion aqueous. So there are certain factors that affect the enthalpy of hydration. What are these factors? First one is the ionic charge. So if the ion has higher charge, that means there will be stronger attraction to water. If there is a stronger attraction to water, that means the enthalpy of hydration will be more exothermic. So the value will be higher in negative charge. So for example, magnesium 2 plus has more exothermic enthalpy of hydration than sodium plus because it only has one positive charge. Also, the ionic radius. So the smaller the radius, the stronger the attraction, which is going to be between the positive ion and the water molecule. So smaller ions like lithium is hydrated more strongly than larger ions like potassium, for example. Generally speaking, ions with high charge density, meaning they are smaller in size and they have higher charge, they will have more exothermic hydration enthalpy. So let's construct the Hesse cycle for the enthalpy of a solution. So we have sodium chloride as solid, and then it will change or be hydrated to give the sodium ions aqueous and chloride ion aqueous. This is the enthalpy change of solution. This is the one that usually they want you to calculate in the exam. You need to construct Hesse cycle using the lattice dissociation enthalpy, which is the formation of the gaseous ion from the solid, and then the enthalpy of hydration, which is the hydration of the ions, the gaseous ions, to form the aqueous ions. As you can see from the direction of the arrows, these two in blue will be one root, and the one in yellow will be the opposite root. Now, there we're going to have root 1 will equal root 2, meaning the enthalpy of solution will equal the enthalpy of hydration of the sodium ion plus the enthalpy of hydration of chloride ion plus the enthalpy of the dissociation of the sodium chloride. Or if they provide you with the enthalpy of formation, it's going to be minus the enthalpy of formation, because enthalpy of formation will be in this direction in this case, and then it will go in the same route with the enthalpy of solution. So please take note of which one they provide you with in the exam. You will do the rearrangement and then you will calculate the enthalpy of solution. The enthalpy of solution is important to determine whether a certain ionic compound is going to dissolve in water or not, because some ionic compounds do not dissolve in water. So if the enthalpy of solution is exothermic or only slightly endothermic, the salt is more likely to be soluble in water. However, there is also entropy, which plays a role. So some solids have positive enthalpy of solution, but they are insoluble in water. So we will talk about entropy as well, because it also plays a role in the solubility in addition to the enthalpy of solution. But generally speaking, if the enthalpy of solution is exothermic or with a negative charge, the solid will be more likely to dissolve, or the ionic compound is more likely to dissolve in water. Some exact tips for this: please use the correct sign, especially for the lattice enthalpy. So lattice enthalpy of formation is always exothermic, but it's positive when we are talking about breaking or dissociation. So take note of which one, and when you construct the Hesse cycle, just put the arrow whether in the direction of formation or in the direction of the dissociation based on what they provide you with in the exam to determine the two routes. You may also ask about to draw the Hesse cycle for the enthalpy of solution, to calculate the enthalpy of solution from data, or explain certain trends like why magnesium chloride is more exothermic than sodium chloride. Remember that magnesium. So what is entropy? Entropy is a measure of the disorder or the randomness of the system. So systems like to have more randomness or disorder, and that will increase the stability. The sample for the entropy is S, and the unit for the entropy is joule per mole per Kelvin. A more disordered systems mean that it has higher entropy, meaning it's more stable. So the more the disorder, the more the entropy and the more the stability. Entropy help to predict whether a certain process will be feasible or not, meaning whether this is going to happen or not. So the increase in the entropy means that we're going to have a higher value for the entropy change. That means that the system or this particular reaction is more likely to take place. So there are certain factors that affect the entropy. The first one is the physical state. So physical states we know is solid, liquid, and gas. Solids are highly ordered, so they have the lowest entropy. Liquids, they have a bit more movement, so they have higher entropy than the solids. And then gases, particles can move freely, so they're highly disordered, so they will have the highest entropy. So the order of entropy, the gas will be the highest, then liquid, then solid. Second thing is the number of particles. The increase in the number of particles or the more the moles of the product of the gas molecules means that there will be higher entropy, not just for gaseous molecule, but also for the liquid. So if you have more of the liquids molecules or more moles, then that means you're going to have higher entropy. The increase in the number of particles will increase the disorder and will give a higher delta S or entropy change. For example, if you have two N2O4 as gas, that gives you two of the NO2 gas. You have two moles of the gas on a product with 1 mole of the gas as a reactant. Then the delta S here is going to be a positive value. There are more moles or more particles, so there will be more disorder and more stability. The third thing is the dissolution. So when a solid dissolves in water, that increases the entropy because the particles will become more mobile. So when you change it from solid to liquid, you increase the entropy, you increase the disorder. So ionic solids, when hydrated in solution, that will give you more disorder and more stability. Entropy change for of a reaction. So to calculate the entropy change for a certain reaction, we need to use the standard entropy. So each substance will have a standard entropy at the standard conditions. So the standard conditions is 298 Kelvin as usual and 100 kilopascal. And the standard entropy is the entropy value under the standard condition for 1 mole of a substance. The value will be given in data book and it's in joule this time, not kilojoule per mole per Kelvin. You can use these to calculate the entropy change in a reaction. So the formula for how to calculate the entropy change for a certain system or for a certain reaction, that will equal the total of the standard entropy of the products minus the total of the standard entropy of the reactants. Usually they will provide you in the exam with the standard entropy of the different reactants and products and ask you to calculate the entropy change. You're going to use the standard entropy value from the data book or from the value they are provided with in the exam. And don't forget to multiply by the number of moles in the balanced equation. So when you do this calculation, you're going to have different number of moles for reactants and product from the balanced equation. So when you do the calculation, don't forget to account for the number of moles. Some example, we have the carbon plus oxygen that gives you carbon dioxide as a gas. To calculate the entropy change, the standard entropy for carbon is 9, for oxygen it's 205, and for carbon dioxide 214. We'll notice that carbon is a solid, so it has a very low entropy, while oxygen and carbon dioxide are gases, so they have higher entropy. Now to calculate the entropy change, this is the total for the products, which is just carbon dioxide 214, minus the total for the reactant, which is 1 mole of carbon and 1 mole of oxygen. That will give us plus 3 joule per mole per Kelvin. And this is the entropy change for this reaction. Gibbs free energy is what we use here to judge whether a certain reaction is going to be feasible or not. So Gibbs free energy link the enthalpy change with the entropy change. So it accounts for both. Not only the enthalpy change will be responsible for whether a reaction is going to take place or not, but also the entropy change. So Gibbs free energy, which is delta G, equals the delta H with the enthalpy change minus the T, which is the temperature of this particular reaction. So in Kelvin, multiplied by the delta S, which is the entropy change. The delta G is the Gibbs free energy change, which is in kilojoule per mole. The enthalpy change is in kilojoule per mole. The temperature is in Kelvin, and the delta S is the entropy change of the system as we have calculated it, and it's going to, we have to change it from joule per mole per Kelvin into kilojoule. So we need to divide the value we usually obtain by 1,000 to convert it to kilojoule per mole per Kelvin. So the feasibility of a reaction, if a reaction has an entropy and Gibbs free energy less than the zero, then the reaction is feasible. So the reaction can occur at this particular temperature. And if it's more than zero, so if it's like endothermic, if it's more like positive side, then it's not feasible at this particular temperature. So what are the factors that affect the feasibility? Some reactions only become feasible at higher temperature because T delta S will increase. So when you have the T delta S, so because delta G equals delta H minus T delta S. So when you increase the temperature and you have the delta S in the positive value, that means this is going to be higher than the enthalpy change, and the total of the delta G will be minus, especially when we talk about endothermic reactions, because the delta H for endothermic reactions is positive. So endothermic reaction can occur at certain temperatures because the T delta S becomes higher value. Eventually, the delta G, as we can see, will become a negative, like an endothermic reaction, which has positive delta H with positive delta S as well. The reaction can become feasible at higher temperature. Some exam tips, always check the units, convert the joule into kilojoule, because this is what we need to do when we calculate the delta G. For entropy of a reaction, don't forget to multiply the entropy values by the moles of the balanced equation. Questions you might be asked to calculate the entropy change of a reaction, as we've seen before, use the delta G to determine the visibility, or explain why the visibility changes with temperature. So how can we decide or determine or calculate the temperature for feasibility? We can calculate the temperature at which a certain reaction becomes feasible if we know the enthalpy change and the entropy change for that particular reaction. In this case, we're going to use the Gibbs free energy equation, but we're going to set the delta G to become zero. So this is the threshold. So this is the minimum value of delta G where the reaction becomes just feasible or the reaction can actually occur. And then when we have the delta G equals zero, we're going to rearrange our equation. You're going to find that the T, which is the temperature in Kelvin, will equal delta H, which is the enthalpy change over the entropy change. For example, if you have a reaction where the enthalpy change is plus 30 kilojoule per mole, so this is endothermic, and then the delta S is plus 100 joule per mole per Kelvin, which is when we divide this by 1,000, it's going to be 0.1 kilojoule per mole per Kelvin. Then the temperature will be 30 divided by zero point 0.1. So that another common question in paper one is about the pH. So the pH is a measure of the hydrogen ion concentration in a solution, and the pH equals, to calculate the pH, it equals minus log 10 of the hydrogen ion concentration. And to calculate the pH, we need to find the hydrogen ion concentration, and we will do that depending on the type of solution. First of all, the strong acids. We have two types of strong acids. We have the monoprotic and the diprotic acids. So monoprotic acids, or strong acids in general, will dissociate to give the hydrogen ion and the anion, or the conjugate base. So if we have a monoprotic acid, this is the acid that will give you only one hydrogen ion per molecule of the acid. The hydrogen ion concentration in this case will equal the concentration of the acid. So because 1 mole of the acid will give you 1 mole of hydrogen ion. So the pH, which is minus log 10 of the hydrogen ion, this will be minus log 10 of the concentration of the ion and of the acid in the solution. Example of that is hydrogen chloride and nitric acid. The diprotic acid, something like sulfuric acid, where each mole of the acid will give you 2 moles of the hydrogen ion. In this case, the hydrogen ion concentration will be 2 times times the concentration of the ion. Again, you can calculate the pH as minus log 10 of 2 times the concentration of the acid. Example is the sulfuric acid. And then we have water. So water as well partially dissociate to give the hydrogen ion and hydroxide ion. And that will allow us to calculate what is called the ionic product of water. Ionic product of water is a constant value for water at a certain temperature. So at certain temperature, the ionic product of water will be a reflection of how much of the water molecule has actually ionized to give the hydrogen ion and hydroxide ion. Ionic product will equal the concentration of the hydrogen ion times the concentration of the hydroxide ion. Sometimes they ask you to calculate the pH of water at certain temperature. They will provide you with the ionic product of water at that temperature. In this case, to calculate or to find the hydrogen ion concentration and the pH. So the neutral water, the hydrogen ion concentration will equal the hydroxide ion concentration, and both of these will equal the square root of the ionic product at that temperature. So the pH can be calculated as minus log 10 of the hydrogen ion concentration. So if you can find the square root of the ionic product, then this is going to be the hydrogen ion concentration, and you can calculate the pH. We can calculate the pH of a strong base using the ionic product of water, because when you use a strong base like sodium hydroxide, it will dissociate completely in water to give you the metal and the hydroxide ion, or the cation and the hydroxide ion. And now if we have a certain base like sodium hydroxide, which has a certain concentration like this one, 0.02 mole per decimeter cube, then the concentration of the hydroxide ion will be considered at the concentration of the hydroxide from the strong base. Now we can use the ionic product of water, which equals the hydrogen ion concentration times the hydroxide ion concentration. The hydroxide ion concentration now is not going to be the similar to the hydrogen ion concentration. It's going to be the concentration of the base. So we can find the hydrogen ion concentration, which is going to equal the ionic product of water, which is going to be provided to you in the question, divided by the hydroxide ion concentration, or the concentration of the base. And then you can calculate the pH as minus log 10 of that hydrogen ion concentration. Note that if you have a base like barium hydroxide, where 1 mole of the base gives you 2 moles of the hydroxide ion, then the concentration of the hydroxide will be double the concentration of the base itself. Now, moving on to weak acids. So weak acids partially dissociate in water to give the hydrogen ion and to give the anion. So we calculate what is called the Ka, or the acid dissociation constant, because it's a reversible reaction. The acid dissociation constant of the acid is similar to the constant for the any reversible reaction. However, the only difference here, because the acids are very lightly dissociate or very partially dissociate in water, so mostly when we put the equation and do the calculation, the concentration of the acid here, which should be the concentration at equilibrium, will be taken as the initial concentration of the acid, because only a small fraction has dissociated to give you the hydrogen ion and the anion. So Ka will equal the concentration of the products of the dissociation, which is the hydrogen ion, and the A minus, or the anion, divided by the concentration of the acid itself. So normally, if the Ka is a larger value, that means we have more of the hydrogen ions concentration, which means that the acid is a stronger acid. So the pKa and its uses, the pKa, we can calculate the pKa in the same way as the pH, which is minus log 10 of the Ka. The lower the value of the Ka means the acid is stronger, and it's useful for comparison between different acids and their strengths. So the higher the value of the pKa, the lower the value of the pKa means the acid is a bit stronger. And then how to calculate the pH of a weak acid. Now we're going to use this equation. We're going to use the Ka value, which is going to be provided to us in the question. And we're going to have also the concentration of the weak acid. So now we can calculate the concentration of the hydrogen ion, because the concentration of the hydrogen ion will equal the concentration of the anion. Now we can put the equation as Ka equals the concentration of the hydrogen ion squared divided by the concentration of the weak acid. And then by rearrangement, the concentration of hydrogen ion will be the square root of the product of the Ka times the concentration of the weak acid. And then finally, pH will be minus log 10, the concentration of the hydrogen ion. So titration and the pH curve is very common in the exam. In 2024, there was a whole long question in paper 3 about the pH curves. So pH curve is when you do the titration. So here you can see that it's titration of the of a strong acid with a strong base. And then with each addition of the titrant, which is the base in this case, you're going to measure the pH of the solution. So it's a curve of the volume of titrant over versus the pH of the solution. As you can see that the pH starts to raise slightly until we reach a point where there is a massive change in the pH with a very small addition of the base. This is the vertical part of the curve, where this is the will give us the equivalent point, or the center of this vertical part will be the equivalent point or the end point of the titration. So these are the different shapes of the curve, the pH curve, based on the type of the acid and base we use for the titration. So if you use a strong acid with a strong base, you can see that you start off with a pH around 1 or 2, and then the nearer the pH 4 or 5, there will be a massive change in the pH with a small addition of the strong base, where the equivalent point will be around 7 here, and then the pH will increase until we reach around 12 or 13 with the excess of the base. And if we use a strong acid with a weak base, like if you use HCl with nitric acid, with ammonia, then you're going to have a start again at 2, and then you can see that there will be also a bit of a change here in the pH, bigger change in the pH nearer the end point when we start to do the complete neutralization. And then the pH will increase here. So the maximum pH will be around 8 or 9, and the endpoint, it will be around 5, pH 5. And then if we use weak acid with a strong base, it's going to be similar to the other one, but now we start at around 3 or 4, and the pH will, at the equivalent point here, would be around 9. And finally, the weak acid with a weak base, wouldn't be this massive change, so they don't have this vertical line if we use weak acid and weak base. The same will apply for the titration of a base with an acid, but the curve will start from the high pH and go until the low pH, because you are adding acid to a base. So it's very important to choose the right indicator for the type of titration we are performing. This is because each indicator has a certain pH range where the sharp change in the color take place. So we have two indicators. The first one is the methyl orange, and methyl orange usually change its color between 3.5 and 4.5. So if we have the end point, or if we have the vertical line passing through 3.5 and 4.5, we can use the methyl orange as an indicator. Otherwise, if it doesn't, then that means the indicator will change its color before the endpoint or after the endpoint. And then we have the phenolphthalein, where it changes its color between around 9 and 10. So for phenolphthalein, if the vertical line passes between 9 and 10, then it would be a good indicator to use. So when we look at the different types of the pH curves, you can see that for a strong acid and strong base, the vertical line will pass through both the methyl orange and phenolphthalein. So you can use any of these two as an indicator for this type. But when we use a strong acid with weak base, titration of a strong acid with a weak base, then you can see that actually the methyl orange will be the best one to use, because the methyl orange will, the vertical line will pass through the pH range of methyl orange, or methyl orange will change its color during the end point or when we reach the end point. However, the phenolphthalein, we would reach the endpoint and the phenolphthalein wouldn't change its color. So the range is beyond the range of the vertical line here. And if we use the mix of a weak acid and a weak base, neither of them can be used. So we cannot use a specific indicator. There will be no charge, no distinct change in the color at the endpoint. In this case, you only can use the pH meter to calculate, to find the endpoint for this reaction. You cannot use these indicators. Finally, when we talk about pH, we have to talk about buffer solutions. So buffer solutions will resist the pH change on addition of a small amount of an acid or a base. So what's the buffer solution? How is it made? It's made of a mixture of a weak acid and a salt of the conjugate base of that weak acid, like acetic acid, or ethanoic acid and sodium ethanoate, for example, or it can be a weak base and one of its salt, like ammonia with ammonium chloride, for example. How does it work? We have the acid, and we know that the acid will partially dissociate in aqueous solution to give the hydrogen ion and the anion. And then we will add some of the conjugate base or of that anion to this acid. So when you add a little bit of an acid, or when you add some acid to the buffer, what will happen is that the reaction will be shifted to the left-hand side to compensate for the excess acid, or the acid that is added will react with the anion. The anion here is going to be in excess because you added the salt, or you added the anion along with the acid. So we have the acid in excess and we have the ion here, the anion in excess. So if you add a little bit more of the acid, then the excess acid will react with the anion. And that will resist the change in the hydrogen ion concentration, basically. And if you add some base, the base will then react with the acid, and that will shift the equilibrium to the right to produce more of the acid. So you will get more of the acid to balance the pH again. So now this is how it works and how it resists the changes of the hydrogen ion concentration or in the pH. So how can we calculate the pH of the buffer? Again, we're going to use the Ka value, or the dissociation constant for the acid. So the Ka will equal the hydrogen ion concentration times the anion concentration divided by the acid concentration. In this case, the anion concentration will be the concentration of the salt that we added, or the conjugate base that we added. So if we are using ethanoic acid with sodium ethanoate, it's going to be the concentration of the ethanoate. And then the HA, this is the concentration of the acid. This is the original concentration of the weak acid as well. Now we can calculate the hydrogen ion concentration by rearrangement. So it's going to equal Ka times the concentration of the acid divided by the concentration. It's essential to know about redox and how to write the half equation and the ionic equation for any redox reaction. So redox is oxidation and reduction. We usually use the term oil-reg, where oxidation is loss of electrons and reduction is gain of electrons. And the oxidation state rules, you need to know these ones because they could be asked about them. So elements of a monoatomic or diatomic, the oxidation state will always be zero. Any neutral compound, the final oxidation is minus 0. The compound ions, something like sulfate, the sum of the oxidation state of all of the atoms within the compound ion will be the oxidation state of the ion itself, which is 2 minus in case of sulfate. Hydrogen usually plus 1, but there is only one exception, which is the hydride, metal hydride, where the hydrogen has an oxidation state of minus 1. Oxygen, it will always be minus 2, but there are few exceptions, which are hydrogen peroxide, where it's minus 1 for the oxygen, or oxygen difluoride, where it's plus 2, or O2F2, where it is plus 1. Halogens normally minus 1, but there will be some exceptions. We will talk about them when the time comes. So how to find or determine the oxidation state of a certain atom in a compound? So we have something like sulfate, and sulfur has various oxidation states. How to find the oxidation state of sulfur and sulfate ion? First of all, the oxidation state of sulfur plus 4 times the oxidation state of oxygen, because we have 4 oxygens. So 4 times minus 2 will equal minus 2, which is the final oxidation state of that ion. Now you can rearrange your equation and you can find that the oxidation state of sulfur is plus 6. How to write the half equation? There are several certain steps or rules you need to follow when you write your half equation so you can write it correctly and easily. So let's practice rather than mentioning these steps. So if we have this redox reaction between hydrogen peroxide and manganate to give you oxygen and manganese, and we want to write the balanced redox equation. First of all, we need to write the half equations. So when we write the half equation, we will write it for the oxidation and for the reduction. Here we have the hydrogen peroxide, where the oxidation state of oxygen here is minus 1. It changed into oxygen, which is 0, meaning the oxygen lost electrons. So this is the oxidation. So now, in order to write the half equation, first of all, we need to balance the atoms. So the oxygen is balanced on both sides because we have 2 oxygens. Need to balance the hydrogen. The hydrogen is balanced by adding protons. So we have 2 hydrogens. So we're going to add 2 protons on the right hand side. Now we need to balance the charge. The charge on the left hand side is 0. On the right hand side, it's 2 plus. So we need to add 2 electrons to make it 0. Now moving on to the manganate. So the manganate here has changed into manganese 2 plus. So the manganese is balanced. Now we need to balance the oxygen. There are 4 oxygen on the left-hand side, so we need to add 4 oxygens on the right-hand side. The oxygen will be balanced by adding water, so we need to add 4 of the water molecules. And now we need to balance the hydrogen. So now we have 8 hydrogens from the 4 water molecules. So we need to add 8 hydrogen ions on the right-hand side. And finally, we need to balance the charge. So on the right-hand side, it's plus 2. On the left-hand side, it's plus 7. So we need 5 electrons on the left-hand side to make it plus 2 like the right-hand side. Now we have these two half equations as we've written them. Now we need to add these two together. Before we add them, we need to balance the number of electrons, so it will be the same for the oxidation reaction and the reduction reaction. So there are 2 on the oxidation and 5 for the reduction. We can make them both as 10 by multiplying the first equation by 5 and multiplying the second one by 2, and that will give us 10 electrons for each of these. Just add the 2 equations, combine these 2 together and simplify. Electrochemical cells is one of the topic that a lot of students find very challenging, and it's very common in paper 1 as well. So I will do my best to simplify this topic for you and give you all the exam techniques or give you all the information that you will need in order to answer the question that comes in the exam. So what is an electrochemical cell? How does it work? What are the components of an electrochemical cell? So an electrochemical cell is these cells which use redox reaction to drive electrons across the cell, and then it can convert this energy into different types of energy. The components of an electrochemical cell is that we're going to have 2 half cells. Each of these half cells will have an electrode of a different metal. And the half cell will be composed of an electrode of a certain metal immersed in an electrolyte, which is an ionic solution of that metal. For example, we could have zinc with zinc ions. So zinc ion, like we can have zinc nitrate, we can have zinc sulfate. So any ionic solution for zinc. And the other one will be a different metal as well, immersed in a solution of ionic solution of that metal, like copper and copper metal. Sometimes as well, we could have a solution that is a mixture of two different ions of the same metal. Like we could have a mixture of iron 2 plus and iron 3 plus, where the redox takes place and these two change in the reaction in the half cell. In this case, the electrode we use is going to be platinum. We don't use iron here. Otherwise, we are talking about a different redox reaction. So we would use platinum and in addition to the mixture of the iron 2 plus and iron 3 plus. When we will connect the two electrodes from the outside with the voltmeter, which can measure the voltage change. And then we can, or potential change, we have to connect the two half cells with something called the salt bridge. So the salt bridge will contain some inert ions. What we mean by inert ions, we mean that ions that will not react with either the first half cell or the second half cell. So basically, it can do like substitution reactions, but it doesn't actually undergo any redox reaction with any of these. Something like potassium nitrate, for example. So potassium nitrate ions will not undergo any redox with any of the ions in either of the half cells. So the role of the salt bridge is to allow the flow through the ions to flow through them and to balance the charges. So as you can see, for example, if we put potassium nitrate, the nitrate will move here and the potassium can move to the other sides to balance the charge on both half cells. So there will be a potential difference that will be generated because there will be on one half cell there will be a reduction a reaction, and on the other one there will be oxidation. So here we have the zinc with the zinc ion. This is called the anode, and the oxidation will take place here on the anode or the negative charge, where zinc will lose electrons to give zinc ions, and the electrons will start to flow through the circuits from outside until it reaches the cathode or the positive electrode, which is the copper, and the reduction will take place here. So here it's the oxidation and here it's the reduction for the copper. So the copper ions will be reduced to give the copper metal. As we can see, we can represent the equation, the oxidation and the reduction. As we can see here, zinc will give you zinc ions plus 2 electrons, and the copper will gain 2 electrons, the copper ion, to give you the copper. We can represent this cell, this electrochemical cell, as follows. So we start with the oxidation reaction first, and we add the species that's going to be oxidized, which is the zinc in this case. And then we add the oxidized form of the zinc, which is the zinc ion. And then we have this line here, this line, vertical line, a small line that refers to the phase boundaries, because the zinc here is a solid and the zinc ion is aqueous. So there is a phase boundary, or there is a phase, these two are in different phases. So you have to show that by adding this small vertical line. And then we have these two vertical lines between the two half cells, and these represent the salt bridge. So this is the salt bridge in between. And then we would write the reduction half cell. So the reduction, where we'll start with the species that's going to be reduced, which is the copper ion, and then don't forget the phase boundary, and then the copper solid. So this is how you represent the electrochemical cell. Start with the oxidation and with the reduction. So how would we know which side is going to be oxidized, which one is going to be reduced? This is based on what we call the standard electrode potential. And the standard electrode potential is that we measure the potential of each mix of ions or redox reaction, how they can actually have the potential to be oxidized or to be reduced compared to hydrogen. So we have a reference electrode with a potential defined as zero. This is the standard hydrogen electrode. And a standard hydrogen electrode, because it's a standard, we have to have standard conditions because the different conditions can affect the standard potential that we calculate. So the conditions here are 298 Kelvin as temperature, 100 kilopascal pressure, and 1 mole per decimeter cubed for the hydrogen ion. The standard hydrogen electrode has the hydrogen as hydrogen gas, and it has hydrogen ion or hydrochloric acid as a source of hydrogen ion with that particular concentration as an electrolyte. And then we have the platinum electrode here, and the platinum electrode where the different reaction can take place or the electrons can move around. And then this is the half cell, and this is connected to the other half cell, which is going to contain the oxidation reaction or the reduction reaction, which we would need to measure its electrode potential. So now we would use, this is used to measure the electrode potential of other half cells. So that will give us the electrochemical series. So an electrochemical series will arrange the different reactions, redox reaction, based on their potential to be oxidized or reduced. When you put the electrochemical cell, we usually write it in the reduction form, meaning we write the reduction reaction, not the oxidation reaction. Remember, these are reversible, but we write it and measure it as a reduction. So as you can see, all of these, the electrons are added here on the left-hand side, meaning these all are the reduction reactions. And then we measure the standard electrode potential. You will get a certain value. The value can vary from being negative charged until it becomes a positively charged. The positive charged electrode potential means that the left-hand side is more easily reduced, or that means this species or this reaction will be most likely to go through reduction. So it's going to be more as oxidizing agent. So here in this electrochemical cell, you can see in front of you, and this is taken from one of the past papers. You can see that the first one, the one with the highest positive value, which is oxygen being reduced to give water, this has the highest oxidizing power, or that means that the oxygen will be reduced. So if you have a half cell for this one with any of the ones below it, this is always going to be the reduction, and the other one is going to be the oxidation. And we can say exactly the opposite for the negative value for the standard potential. So the ones with the negative value, that means the right-hand side is more easily oxidized, meaning it will be more towards the oxidation. So the reaction will go the other side to the other side. So it's going to be oxidation rather than reduction. So as you go down from most positive to most negative, then the oxidizing power will be reduced, and as you go from the bottom to the top, from the most negative to the most positive, the reducing power would be reduced. So these at the bottom here with the most negative are the highest reducing, so there will be mostly oxidized. And these at the top with the highest positive charge will be the highest for to be the highest oxidizing, or they will be mostly reduced. So it's going to be reduced. Remember that thing that is reduced is oxidizing agent. The thing that is oxidized is a reducing agent. And now we will calculate the EMF for any cell. The EMF should always be positive for a reaction to be feasible, for electrons to flow. How to calculate the EMF? We calculate the EMF using this equation. So we're gonna calculate it using the standard electrode potential for the reduced one minus the standard electrode potential potential for the oxidized half cell. So which one is reduced, which one is oxidized? The one that is reduced is the one with the more positive charge. The one which is oxidized is the one with the more negative charge. Or more generally, you could say that the one that is reduced will have a higher value of the standard electrode potential than the one that is oxidized. So for example, one of the exam question was asking why zinc, the zinc here, can actually be used to reduce vanadium 3 plus to vanadium 2 plus, but cannot reduce vanadium 2 plus to vanadium. To answer this question, you can look at the standard electrode potential for the reduction reaction from vanadium 3 plus to vanadium 2 plus, and you can find the standard electrode potential is 0 minus 0.26. And this is more than the standard electrode potential for the reduction of the zinc 2 plus to zinc. This is the zinc 2 plus to zinc. That means zinc can reduce the vanadium, but the vanadium can vanadium 3 to vanadium 2, but the vanadium 2 plus cannot do the other side. On the other hand, when you look here, you can find that to reduce vanadium 2 plus to vanadium, you would need something that would have a standard electrode potential that is lower than minus 1.2. And you can see that the zinc, the standard electrode potential for it is higher value. So it cannot be used to reduce vanadium 2 plus to vanadium. So what can be used from this table? It's magnesium. So you can use magnesium because the standard electrode potential for it is actually less than the standard electrode potential for the vanadium 2 plus to vanadium. And now we can calculate the EMF or electromotive force of the of this of any cell. So let's say we are going to calculate it for the vanadium 3 plus to vanadium 2 plus along with the zinc. Then it will be, now we know that this is the reduction and this is the oxidation. So it's going to be the standard electron potential for the reduction, which is minus 0.26. And then this is minus the standard electrode potential for the one that is oxidized, which is the zinc. So it's minus 0.76. And then you can actually calculate that and find the EMF for this particular cell, which is 0.5 volt. As you can see, it's in the positive value, which means this can actually be feasible. So what are the different things that can affect the EMF? In the exam, they wouldn't ask you to explain why the change in the concentrations affect the EMF, but they will ask you what would be the effect. So I'm only going to tell you what is the effect without explanation because you don't need to know it at this point. So we have two half cells. So we have the half cell where the reduction take place. So the reduction which happens at the cathode or the positive electrode. So if you increase the concentration of the half cell or the ions at the half cell where the reduction take place, that will lead to an increase in the EMF and vice versa. So if you decrease the concentration of the solution at the reduction, that will decrease the EMF. And we can say the opposite for the oxidation. For the oxidation reaction, if you increase the concentration of the ion at the anode where the oxidation takes place, then that will decrease the EMF value. And vice versa again. So if you decrease the concentration of the ions at the anode, that will increase the EMF. Also, the pressure can play a role. So increasing the pressure will decrease the standard electrode potential. This is why we need to measure everything under standard conditions. So the standard electrode potential, as we said, this is how we calculated. So the standard electrode potential, because this is very common in the exam, not just in paper one, but also in paper three in the multiple choice questions. Now we should know how to calculate that and then how to write the equation for how to write the representation of the cell. So as you can see here, we have two reactions. The first one is the oxidation of iron to iron 2 plus, where we have the iron as a solid. So this is the half cell where the oxidation takes place, and then we added the phase boundary. And then this is the salt bridge, and then this is the other reaction where the reduction takes place. So we start with the species that is going to be reduced, and then the reduced form. These two are aqueous. None of them is in a different in a different phase. So we didn't add a phase boundary here. We just added a comma in between these two, but we have an electrode of platinum. Even if they didn't say it, you can state it, then you will have to say it in the representation. We added the phase boundary and then we added platinum at the end because we will have to have a certain electrode, which is mostly platinum. So this is how to write it. And it's very common in the exam to ask you to give the conventional representation of the cell. Then the commercial electrochemical cells, the one that mostly come in the exam are the rechargeable one, the lithium ion batteries, and the fuel cell or hydrogen fuel cell. So lithium ion are these rechargeable cells which you can use and then you can recharge like the one that you use with your laptops or with your mobile phones. So the electrodes here for the lithium ions are you have a positive and negative electrode or a cathode and anode. So the positive electrode or the cathode is lithium copper oxide, and the negative electrode here is graphite. The electrolyte is lithium salt in organic solvent. So there are two equations here, and both of these we're gonna write them in the reduction form because we're gonna refer to the standard electrode potential. So the lithium plus will be when reduced, it will give you the lithium atoms. And then the other one is the lithium ion reacting with the copper oxide and gains electrons to give lithium copper oxide. And the standard electrode potential for the first one, as we can see, is minus 3.04 volt. This is and the second one is plus 0.56. So which one is going to be oxidation? Which one is going to be reduction? This one has lower value, more of a negative charge. So this is going to be the oxidation, as we can see. And the other one is the reduction. So what happens at the anode here? We're going to have to write the oxidation. So it's lithium giving you the lithium ions plus the electron. So this is what happens at the anode, and the other one at the cathode will be this reduction reaction. And then what happens in the recharge? When you recharge the battery, you reverse the both reactions. So the oxidation will be reduction, and the reduction will be oxidation in order to reverse these two reactions and then recharge the battery. And then finally, the hydrogen fuel cell. So hydrogen fuel cell will use hydrogen and oxygen to give water and generate electricity. So in this case, we're going to have the hydrogen, which is going to be fed into the anode and the oxygen into the cathode. So the hydrogen at the anode is going to be oxidized, and you need to know the equations, half equation. So hydrogen will be oxidized here by reacting with the hydroxide ion because the electrolyte here is potassium hydroxide. It's alkaline hydrogen fuel cell, and that will give you water and electrons. And then the oxygen, on the other hand, will be reduced by reacting with water and with the electrons to regenerate the hydroxide ion. The overall equation for that will be hydrogen plus oxygen gives you water. And whether we use the alkaline electrolyte or alkaline hydrogen fuel cell or acidic hydrogen fuel cell, the potential will be always the same because the overall reaction is the same because this was one of the past paper questions. The hydrogen fuel cells have their advantages and disadvantages. So what are the advantages? The advantage is that you don't need to recharge it. So as long as you have a continuous supply of hydrogen and oxygen, you're going to generate electricity. The electricity is generated and water is the only waste product. You don't have any carbon dioxide here like the combustion engines. Also, it converts most of its stored energy into kinetic energy. So no heat energy waste like the combustion engines, and it's more environmentally friendly. However, when we say that the only waste is water, there is no carbon dioxide, it doesn't mean that it's carbon neutral. Why? Because the hydrogen and oxygen that itself that we use, they can be generated from the electrolysis of water, and the electrolysis of water would need to use electricity, and to use electricity, you need to burn fossil fuel, which means you would need to produce carbon dioxide, so it's not absolutely carbon neutral 100%. And also one of the challenges with the use of hydrogen fuel cell is the cost of production and the storage and transport for Group 2 elements or alkaline earth metals, or the group 2 elements are S block in the periodic table, and they all have the configuration end with an S2, where N is the number of the period. And that includes elements from beryllium until radium. The physical properties, they have high melting points and boiling points, of course, because they have metallic bonding, they have low density, and they all form 2 plus ions. So let's look at the trends down the group. First of all, atomic and ionic radius will increase down the group because there are more electron shells. And then ionization energy will decrease down the group due to two factors. The first one, the outer shell electrons are further away from the nucleus due to the increase in the radius and increase in the shells. Also, because there are more inner shells, there will be more shielding, so the outer shell electrons are easier to remove. Finally, reactivity. Reactivity is related to the ionization energy or to how easy we can remove the electrons. And since the ionization energy decreases down the group, reactivity as well increases down the group because the electrons will become easier to remove. So in terms of their reactions, they react with oxygen to give metal oxides, which have the formula MO2. And these oxides are solid, white solids. The reactivity, as we said, increases down the group. So barium will burn more vigorously than magnesium with oxygen. The reaction with water, they will react with water to give metal hydroxides and hydrogen gas. The reactivity increased down the group. So we have magnesium that react very slowly with water, and it reacts mainly with steam or react faster with the steam. And when magnesium reacts with steam, so water as a gas, it will give magnesium oxide rather than magnesium hydroxide and hydrogen. And the reactivity with water will increase down the group, and so calcium, strontium, and barium will react more vigorously with water. Solubility trend, we have the solubility for the hydroxide and sulfate. So for the hydroxide, solubility increases down the group. So magnesium is insoluble, magnesium hydroxide is insoluble. And then as you go down, solubility increases. So barium hydroxide completely soluble in water. And then solubility trend for sulfate, it's the opposite. So solubility decreases down the group. So you have magnesium very soluble, magnesium sulfate very soluble in water, and barium sulfate is insoluble. And we use the test for sulfate using barium. So if you want to test for sulfate, you can use barium chloride. As well as if you want to test for the barium, you could use sulfuric acid or a sulfate salt where there is displacement reaction and you form barium sulfate as a white precipitate. The uses of group 2 elements and their compounds. Magnesium is used for the extraction of titanium, and this equation is quite common in the exam, where titanium tetrachloride with magnesium will give you titanium and 2 of the magnesium chloride. Magnesium hydroxide, it's used in indigestion remedies because magnesium hydroxide will neutralize the acid in stomach. Barium sulfate is used in barium amines for medical x-rays because it's insoluble and it becomes safe because it's not absorbed, and it can be used for the x-ray because it's opaque for the x-ray. Calcium carbonate and calcium oxide remove the sulfur oxide or sulfur dioxide from the flue gases, and the reaction between calcium oxide with water and sulfur dioxide will give the calcium sulfide, which is Group 7 elements exist as diatomic molecules, and each atom will have 7 outer shell electrons, 2 in the S subshell and 5 in the P subshell. They are colored, they are nonmetals, and they exist as simple molecular substances. The boiling point of these will increase down the group. This is because the size of the molecules or the size of the atom becomes bigger, and then that means the van der Waals forces of attraction that between the molecules will increase and would need more energy. So the boiling and melting point increases down the group. The trend down the group, first of all, the atomic radius always increases down any group because of the increase of the number of shells. Electronegativity will decrease down the group, and this is because the outer shell electrons are further away from the nucleus because of the increase in the atomic radius, and they become more shielded. So they will attract the or pull the electrons in a covalent bond less than the ones at the top. Reactivity as oxidizing agent, meaning gaining of the electron, that will decrease down the group. And this is because it becomes harder to gain an electron down the group due to the increase in the distance between the outer shell electrons and the positively charged nucleus, and also because of the shielding. This is why we have these displacement reactions where a more reactive halogen displaces a less reactive halide from its solution. So we have the chlorine will displace both the bromide and iodide to give a chloride solution and to give bromine or iodine. That leads to a change in the color of the solution when you add when you add chlorine to either potassium bromide or potassium iodide because of the release of the bromine, which turns the solution orange, or the release of the or formation of the iodine, which turns the solution brown. In the same way, bromine will only displace the iodide, but not the chloride. And finally, the iodine will not displace either of the two. Reaction with cold dilute alkali. This is a very well-known reaction, and it's very common in the exam to ask you what is the reaction between chlorine and a cold dilute alkali. So chlorine react with sodium hydroxide to give the sodium chloride, sodium chlorate 1, and water. Here, this is called a disproportionation reaction. Disproportionation reaction is this type of reaction when the same substance gets oxidized and reduced in the same reaction. So chlorine here has an oxidation state of 0, and then it will give you the chloride, it's sodium chloride, with an oxidation state of -1, which means this is got reduced, and in sodium chlorate 1, the oxidation state of the chlorine is +1, meaning this got oxidized. So the same chlorine here got oxidized and reduced in the same reaction. The sodium chlorate 1 that is formed is used as bleach, and these are very well known and common type of question in the exam. Reaction with water. Chlorine react with water in two types of reaction. Both of these will be redox reaction. The first one is disproportionation reaction, where chlorine react with water to give two acids, which are hydrogen chloride and hydrogen chlorate 1. These are the two acids. Again, this is disproportionation because the chlorine was oxidized and reduced. Chlorine NaHCl was reduced because the oxidation state -1, and chlorate 1, it's +1. So this is oxidized. This is why we use chlorine for water treatment, because the the chlorate 1 the hydrogen chlorate 1 can be used as antibacterial. So we add a tiny bit of chlorine or some chlorine, not too much of chlorine, to water to kill the bacteria. And it's only added in small quantities because chlorine itself is poisonous, it's toxic. So when people drink water, if they have a lot of chlorine, they may get poisonous. But we need to balance between the risk of not using chlorine to sterilize water and kill bacteria, and the risk of actually the potentiality of someone getting poisoned by the excess of the chlorine. And because the benefit outweighs the risk, chlorine is used in water, and they only add small quantities anyway. Also, chlorine can react with water under UV to give hydrogen chloride and oxygen. This is not a disproportionation reaction. In this case, the oxygen from water is the one that is get oxidized to oxygen, and the chlorine gets reduced to chloride and hydrogen chloride. In the exam, if they simply ask you about the reaction between chlorine and water, you can mention any of these two. But if they have more specific question, like what is the reaction, which reaction that would produce two acids, then you have to mention the disproportionation reaction, even though this is a correct reaction between chlorine and water, but this is not the reaction they are looking for if they want the two acids. Then we need to talk about the trends in reducing power of the halides ion. So if the halogens as oxidizing agent, their activity decreases down the group, that means that the reducing power of the halide down the group will be the opposite. So it will increase. That means as you go down, the reducing power increases. So when we talk about halides, which are chloride, bromide, and iodide, they can act as reducing agents. When they act as reducing agent, they get oxidized to the halogen. Fluorine will be the least reactive. And fluoride, by the way, is also it's above chloride, or fluorine is above chlorine. So the fluoride even less reactive than the chloride itself. So fluoride as a reducing agent is less reactive than the chloride. So for fluoride and chloride, both of these, when they react with sulfuric acid, they will only act as a base, because they will give you, if you react sodium chloride with sulfuric acid, that will give you hydrogen chloride and sodium hydrogen sulfate. So the role of the chloride here will be a base, because it will take the proton or take a hydrogen from sulfuric acid, or it will accept a proton. So now this is not a redox reaction. But if you react with sodium hydrogen bromide or sodium bromide with sulfuric acid, it will now turn into a redox reaction. The bromide will get oxidized to give bromine. At the same time, the sulfur in the sulfuric acid will get reduced, and it will give you sulfur dioxide. The reaction will stop at this stage. So it will only be reduced to sulfur dioxide. Remember that the oxidation state of sulfur in sulfuric acid is +6, but in sulfur dioxide it's +4. So it was reduced. This is because it has a certain reducing power. Iodide has even a stronger reducing power. So the iodide, when it actually reacts with sulfuric acid, it can reduce it even further, not just to give sulfur dioxide, but also to give hydrogen sulfide, H2S. So now you can get two different gases that contain sulfur when you react the iodide with sulfuric acid. One of them is sulfur dioxide, the other one is hydrogen sulfide. And of course, the iodide will get oxidized to give the iodine. How to test for the halides? To test for the halides ions, we have the silver nitrate test. So first of all, you need to add dilute nitric acid and then add silver nitrate. Why do we need to add a dilute acid first? Because we need to exclude the presence of any carbonate in the solution. So if there is any carbonate with silver nitrate, it will give a precipitate of silver carbonate. So we need to exclude the presence of carbonate. So you add dilute acid first. If there is any carbonate, it will react to give you carbon dioxide and water. So you add the acid and then you add silver nitrate. Fluoride will not give you any precipitate, so there is no visible change. You're not going to see anything. In case of chloride, you will see a white precipitate. In case of bromide, there will be a cream precipitate. In case of iodide, there will be a yellow precipitate. You can even test these further by adding ammonia. So you can add ammonia solutions to the precipitate and see what happens. With chloride, if you add dilute ammonia, the precipitate will dissolve in dilute ammonia. The bromide and the silver bromide and silver iodide that were formed from the chloride and bromide with silver nitrate will not dissolve in dilute ammonia. However, if you add concentrated ammonia, you can see that the silver bromide precipitate will dissolve. The silver iodide will not dissolve in either, so it will not dissolve in dilute ammonia or in concentrated ammonia. This is how we differentiate between the three halides. And very quickly, the tests that you need, the chemical tests that you need for paper one. We talked about the test for halides. Now let's talk about the test for sulfate. So sulfate is the test with barium salt. So you use barium chloride added to the sample, which has the sulfate. If there's a white precipitate form, then it's sulfate. But before you add the barium chloride, you need to use acidified barium chloride, or you need to use dilute hydrochloric acid first, also to exclude the carbonate, because barium carbonate is a white precipitate as well. Test for carbonate: if you add any dilute acid like hydrochloric acid, carbon dioxide will be produced, and then if you bubble this gas through lime water, the lime water will turn cloudy. So this is a known test for carbonate and for carbon dioxide. Finally, tests for the cations. We have a test for group 2 ions first. So we have the flame test. You need to know only these three. Calcium and flame test will give you brick red flame. Strontium will give you red flames, and barium will give you pale green flames. The test was the hydroxide. So test was sodium hydroxide, for example. We know that magnesium will give you a white precipitate. Calcium will give you a slight white precipitate, not really a strong precipitate, and strontium as well, because they tend to be more soluble in water now. With barium, there will be no visible change because barium hydroxide is soluble in water. Finally, test for ammonium ion. So the ammonium ion, if you add sodium hydroxide, period three elements and their oxides. Period three elements are the elements from sodium to chlorine. They have a changing characters from being metallic to more non-metallic characters, and they all have the same number of electron shells. The trends across the period: first, the atomic radius will decrease across the period. This is because there are more protons as you go to the right, so there will be stronger nuclear attraction. Ionization energy generally increase, but there is a slight drop at the aluminium because the electron now is being removed from the 3p orbital, which is further away from the nucleus and more shielded with the extra 2s or 3s orbital. And for sulfur as well, because in comparison with phosphorus, sulfur, the electron is removed from paired electrons from suborbital with paired electrons. So there is some repulsion between the electrons compared to the phosphorus. The electric conductivity, so they will be high with the metals, silicon as semiconductors, and the non-metals, phosphorus, sulfur, and the chlorine, they are non-conductors. Melting and boiling point, so from sodium to aluminum, there will be high melting point. This is because they have metallic bonding, and the melting point will increase in strength as you go to the right because there is an increase in the positive charge from +1 to +2 +3, and there is an increase in the number of delocalized electrons as well, and decrease in the radius. So there will be stronger attraction between the delocalized electrons and the positively charged ions. Aluminium has a bit of non-metallic character, so you don't see massive change in the boiling points between magnesium and aluminium. And then you can see that silicon has a very high melting point. This is because silicon exists as a giant covalent structure, which means that in order to melt silicon, you need to break these bonds. The covalent bonds are very strong bonds. In case of the non-metals, which are phosphorus, sulfur, and chlorine, these are all non-metal, exist as simple molecular structure, and they have weak van der Waals forces of attraction. However, as you can see, that sulfur has the highest melting out of these because sulfur is the molecule of sulfur is S8, meaning it has S atoms of sulfur. Phosphorus is 4 and chlorine is only 2. So the increase the number of the atom in the molecule means that the van der Waals forces of attraction will be stronger and it will need more energy to break the bonds. This is why this trend where sulfur has the highest out of the three, the phosphorus and then chlorine. Reaction with oxygen for the group 3 period 3 elements, they react with oxygen to give you the oxides. So sodium will give you sodium oxide, magnesium oxide, aluminum oxide, and silicon oxide. As we can see, the only one that you need to memorize because it doesn't follow what you expect is the reaction between phosphorus and with oxygen, because the formula of this oxide is P4O10. It's not the expected P2O5. Structure of the oxides. So sodium oxide and magnesium oxide will have giant ionic structure because they are completely ionic. Aluminum oxide is giant ionic, but it has some covalent character. The silicon oxide has a giant covalent structure, so it will have a very high melting point. And then phosphorus oxide and sulfur oxide, they are simple molecular structures. So they are basically, the sulfur is a gas, so they have low boiling points. Acid-base nature of the oxide. So we know that the metal oxides are basic and the non-metal oxides are acidic. So sodium oxide is basic. When it dissolves in water, it will give a pH in the range between 12 to 14. Magnesium oxide is less basic when it dissolves. Magnesium oxide doesn't, magnesium hydroxide is not soluble in water, as we know. So magnesium oxide is, although it's basic, but it has a lower pH, so it's between 9 and 10. Aluminum oxide is amphoteric. It's insoluble in water and can react as an acid or a base, and we will talk about that. Silicon dioxide is weakly acidic, however, it's insoluble and it's giant covalent structure, as we know. Phosphorus and sulfur dioxide, when they dissolve in water, they will produce the acids. They are non-metallic oxides and will give a pH in the range between 1 and 3. So oxide reactions with water, as we know, sodium will give you sodium hydroxide, magnesium will give you magnesium hydroxide, phosphorus oxide, when it reacts with water, will give you phosphoric acid, and sulfur dioxide will give you sulfurous acid or sulfuric 3,4 acid, and then sulfur trioxide will give you sulfuric acid. Aluminium oxide and silicon oxide are insoluble in water. However, aluminium oxide has an amphoteric behavior, meaning it can react with an acid and act as a base to give salt and water, and also can react with a base to act as an acid to give salt. So we have aluminium oxide with hydrogen chloride will give aluminium chloride and water in a neutralization reaction. So it acts here as a base. And then when you react it with sodium hydroxide, with excess of sodium hydroxide in presence of water, will give you that molecular structure that will give you that structure, this ionic compound, which is sodium and aluminium with four of the hydroxide ion. And so it acts here as an acid. Reaction of oxides with acids and bases. The basic oxides will react with acids to give you salt and water. So magnesium oxide with hydrochloric acid will give you magnesium chloride and water. And acidic oxide with bases as well will react to give you salt and water. So sulfur will give you sodium sulfide. Sulfur dioxide with sodium hydroxide will give you sodium sulfide and water. And then the phosphorus with sodium hydroxide will give you sodium phosphate. And the deep block elements in the periodic table are called the transition metals, and they all have these properties of being able to form different ions with a different oxidation state. They can have a partially filled the subshell. The scandium and zinc, the two elements which are at the beginning and the end of the 3D block, they are not considered as transition metals because they only have one oxidation state. So what are the properties of transition metals? They have four properties, which we are going to talk about in the discussion of the transition metal. The first one is having a variable oxidation state and then being able to form colored ions. They act as catalysts and they form complex ions. So let's start by talking about the complex ions. So what are the complex ions? Complex ions formed of a central metal ion surrounded by ligand. These ligands will donate lone pair of electrons to form coordinate bonds or dative covalent bonds. So according to how many of the ligands can surround the central atom, the shape of the complex ion will change. So we have four different shapes of the complex ion. The first one, when we have small ligands like ammonia or water, each of these will have lone pair of electrons either on the nitrogen or the oxygen, and they can actually donate these lone pair of electrons and form a coordinate bond or dative covalent bond with the central atom. Then we can have up to six of these small ligands around the central atom, and the shape will be octahedral. When the shape is octahedral, the bond angle here is going to be 90. So some examples of that, when we have the ferric ion or the iron 3 plus ion, and it's surrounded by six molecules of water. Each of these molecules will give you a coordinate bond with the central ion, and that will give you the complex, and this complex will have a charge. The charge here will equal the total charges of all of the molecules making that complex, or all of the particles making that complex. So we have the iron has 3 plus, because it's an ion, 3 plus charge. The water molecules, they are neutral, they don't have a charge, so the total charge of the complex ion here will be 3 plus. And then we have something like copper. We could have more than one of these ligands surrounding the central ion. So copper could have up to 4 of the ammonia and 2 of the water surrounding the copper, and that will give us this complex ion. Again, it's going to be octahedral because in total there are 6 of the ligands surrounding the central ion. The charge here will be 2 plus because this is the charge of the copper and all of the ligands are neutral. If we have something like chloride, chloride also can act as a ligand, and chloride here is an ion. It's bigger in size, and the maximum number of chloride that can surround a central atom or a central ion is 4. So the maximum number of the ligands around the central ion will be 4, and the shape here will be tetrahedral, and the bond angle will be 109. Some examples of these is the copper surrounded by 4 of the chloride, so copper Cl4, and the charge here again will depend on the charge of these ions. So the copper is 2 plus, and we have 4 of the chloride, each with 1 minus, so in total there are 4 minus, so the final charge will be 2 minus for that complex ion. And then we have something like copper chloride. It's the same as well, 4 of the chloride surrounding the cobalt ion, and the cobalt is 2 plus, 4 of the chloride, each with 1 minus, so in total 2 minus. Also, we could have 4 of the ligands surrounding a central atom or a central ion, and we end up with a shape, a square planar. And this is an exception. It's different from the tetrahedral, and you need to know that exception, which is the cisplatin or the platinum. So when you have platinum and it's surrounded by 4 ligands, 2 of these are chloride ion and 2 of these are ammonia, and you end up with this complex ion, and the shape of it is a square planar rather than tetrahedral, and the bond angle here is 90. There are 4 ligands. Sometimes you could have maximum of 2 ligands surrounding the central ion, like silver with 2 of the ammonia. In this case, the shape is going to be linear because there are only 2 ligands surrounding the central ion, and then also the charge will depend on the charge of the different components of this complex. So the silver is 1 plus and the 2 ammonia are neutral. So in total, there will be 1 plus. The types of ligands. We have 2 different types of ligands. We can either have a monodentate ligand. A monodentate means a ligand that can only donate 1 lone pair of electrons to form only 1 coordinate bonds. Examples of these is water, ammonia, and chloride. And then we have the bidentate or the multidentate. So bidentate ligands means that they can donate 2 different lone pair of electrons to form 2 different covalent bonds or coordinate bonds with the central atoms. Examples of these are the ethane 1,2-diamine, like this one. So we have 2 amino groups here with 2 nitrogen. Each of these nitrogen can donate the 2 electrons in a coordinate bond and will form a coordinate bond or dative covalent bond with the central atom. That means it's bidentate. And also we have the ethane diuate, which is 2 carboxylic acid basically linked to each other, or carboxylate, and the charge of this is 2 minus. The 2 oxygens with the negative charge, each of these can donate the lone pair of electrons and can make 2 dative covalent bonds. And then we have the multidentate one, like ADTA or EDTA. This is the structure of the EDTA, which has 2 nitrogens here and has 4 of the oxygens with a negative charge. All of these 6 atoms can donate lone pair of electrons to form 6 different dative covalent bonds with the same central atom. So this is called a multidentate. Some of the examples, or sometimes in the exam, they ask you to draw the complex of a certain ion with one of the bidentate ligands. So for example, to draw something like that, we have here a central ion of iron 3 plus, and we have 3 of the ethane diuate ions. Each of these will make a dative covalent, 2 dative covalent bonds with with the central ion, as you can see. And in total, the three molecules that are surrounding the ion, because the maximum will be six dative covalent bonds surrounding the central ion. So the three will have a total charge of six minus, because each of these will have two minus charge. And we have the ion has three plus, so the complex ion itself has a total charge of three minus. The displacement or replacement of the monodentate ligand with a multidentate or a bidentate ligand is called chelation. So chelation is when a bidentate or multidentate ligand substitute or replaces a monodentate ligand around a central around an ion. And now the new complex that is formed will be more stable. Why would it be more stable? It will be more stable because there will be more particles produced at the end, because you are replacing six particles or six ligands with either three in case of bidentate or with only one in case of the multidentate, especially if it has six different, can make up to six different dative covalent bond like EDTA. In this case, if you have as a product a larger number or higher number of particles, that means the system will be more stable because the entropy will increase. So when we talked about the entropy, the degree of randomness or the disorder, it increases with the increase of the number of particles. So basically, if you say you are replacing the six water molecules surrounding an iron with a DTA or with EDTA, then you are moving from having two particles on the left-hand side into having seven, because there is now the complex ion and six of the water molecule. So there will be an increase in the entropy, or the entropy change will be more positive. So this is why it's more stable. Isomerism of the complex ions. So complex ions can form different types of isomers. The first one is the optical isomers, and optical isomers can be seen in case of octahedral complexes when they have three bidentate ligands. So something like chromium with three of the ethane diamine ligands. So as you can see here, you can have non-superimposable mirror image of these two to give you the optical isomers. So this is a mirror line, and these are the two complex ions. So these are optical isomers. And then we can have the cis and trans. There are two cases for the cis and trans isomers. The first one is with octahedral complexes when they have four monodentate ligands of one type and two monodentate ligands of a different type. In this case, we can have either a trans, the isomer, where the two ligands, which are the odd ones or the different ones, are opposite to each other. Can you see the cobalt one, which has four of the water and two of the chlorine? The two chlorines here are opposite to each other, so this is the trans isomer. And then we can also have the cis. In this case, the two odd ones will be next to each other. So this is the cis and this is the trans. Another one is the one that we can see in the square planar complexes when it has two pairs of ligands. So we have two different ligands. Each of these will have will have a pair of the same type. So something like platinum, platin, cisplatin, and transplatin. So cisplatin, as you can see, there are two of the chlorine and two of the ammonia, or two of the chloride and two of the ammonia. And then if the two chlorines are, or the two similar ligands are next to each other, then it's going to be the cis isomers. And if the two, which are one of the main properties of the transition metals is the ability to form colored ions. So why the transition metal are able to do that? So the colored ions or the colored complex come from the d-d electron transition. So when they have ligands surrounding them, the ligand can split the d sub-level into two energy levels. And then electrons can gain energy by absorption of light from the visible region, and then this will cause the excitation of the electrons from an energy level to another energy level. The color that you see is the complementary color, or the part of the light that was not absorbed. So this is called the complementary color. So the color of the complex of the transition metal will depend on four things. The first thing is the metal ion itself. So depending on which transition metal we are using. The second one is the oxidation state of that metal ion. So you could be using the same metal ion, but with different oxidation state, and that will give you different colors. And then the ligands, so different ligands will give you different colors. And finally, the coordination number, whether you're gonna have two, four, or six ligands surrounding your central atom. So you can change if you use the same ligand. You can change the color of the complex if there is a change in the oxidation state, or if there is a change in the ligand used, or if there is a change in the coordination number. And this is one of the typical questions in paper one. They could ask you, how can you change the color of the colored complex? We can use spectroscopy to find the concentration of the transition metals. So transition metal ions usually form these colored solution due to the dd electron transition. The amount of energy that an electron absorb in order to actually be excited from one level to another can be calculated. So the delta E, or this energy that was absorbed, equal the Planck constant times the frequency, and the frequency is in second minus one on in hertz. We can also find it by the Planck constant times the speed of light divided by the wavelengths of the light that was absorbed. So the wavelength is usually, we find it in meter, but it's usually provided to you in the question in nanometer. In order to convert from nanometer to meter, you have to divide by 10 to the power of 9, or multiply by 10 to the power of minus 9. So the intensity of the color produced is related to the concentration of the ion in the solution. So we can use colorimetry or UV visible spectroscopy to quantify this, to find the concentration of an unknown sample. How can we do this? And that was a long question in paper 3 in 2024 exam. The steps are, first of all, you need to prepare a series of a standard solution of known concentration of the transition metal ion complex. So first prepare different concentrations, and then use the spectroscopy, the visible spectroscopy, or the colorimeter to measure the absorbance. And absorbance here is how much of the light was absorbed. Measure the absorbance of each concentration, and then you need to plot that the absorbance versus the concentration, or concentration versus absorbance, and this is called a calibration curve. That will give you a straight line, as you can see here, this blue line here. So it's a straight line between the absorbance and the concentration. Then you will measure the absorbance of the unknown sample, find the absorbance, and then find this curve to find the concentration of your unknown solution. This is how you find the concentration of an unknown solution of a complex ion or of a transition metal. Ligand substitution reaction. So one ligand can be replaced by another ligand. This is usually, as you can see here, a reversible reaction. So this is a reversible process. For example, you could have the aqua ion of the copper, which is surrounded by 6 molecules of water reacting with ammonia. That will give you this colored complex here, which is the copper with the 4 of the ammonia and 2 of the water, releasing 4 of the, or substituting 4 of the water molecules. With a chloride as well, you could have the copper with the water, and then that will, with 4 of the copper, that will give you the copper surrounded only by 4 of the chloride, because we know that chloride can only, we have the maximum of 4 ligands of the chloride because of their size, and they will replace the 6 ligands of water. Now the new complex has a different shape, because there is a change in the coordination number. Different ligands can form different strengths bond. So ligand substitution is easily reversed, because you can see it's a reversible reaction here. However, there sometimes the new complex that is formed is more stable than the previous one. And this could be because one of two things. The first thing is the chelation effect. And chelation here is when bidentate, as we said, or multidentate ligand substitute monodentate ligands. And then there will be more stable complex because there is an increase in the entropy of the system because there are more number of particles as products. Or in case of the ligand forming a stronger bond with the metal. For example, when we have the iron 3 plus ion and cyanide, the cyanide can form a stronger bond with the iron than the water. So when you have the aqua ion of the iron 3 plus ion, and we have the cyanide, the complex formed here will be more stable. This is why the reaction will be pushed more. Hemoglobin inside our body is a complex ion as well, which is formed of a central atom or a central ion of iron 2 plus, and the iron 2 plus have around it six different coordinate bonds coming from three different ligands. Four of these will come from the same molecule called the heme. One of these will come from another protein called globin, and then the sixth one will come either from oxygen or from water. So the iron can, or this complex, they can form this coordination bond with oxygen, and or the oxygen can form a coordination bond with the iron or with the hemoglobin, and it can be transferred around the body. It will give the oxygen to the tissues, and then this is going to be substituted by the water molecules. However, when you have carbon monoxide, we know that carbon monoxide is poisonous. And the reason why carbon monoxide is poisonous, because if you take carbon monoxide, then the carbon monoxide is able to make a coordination bond, which is much more stable than the coordination bond between the hemoglobin and the oxygen. And carbon monoxide will replace the oxygen and it will form carboxyhemoglobin, which is much more stable complex. So the oxygen cannot now bind to the iron or even the water. So this is why there's when you have carbon monoxide poisoning, you end up with suffocation because there isn't enough oxygen around your body. Variable oxidation states for the transition metal ions. So we know that transition metal ions exhibit multiple oxidation states. For example, manganese can have from +2 up to +7. Iron can have two of these, which are +2 and +3. The stability of these different ions will depend on the ligand, or the complex ions with these ions will depend on the ligand and the pH. So transition metals can act as catalysts. A catalyst will speed up a chemical reaction by providing an alternative reaction pathway with a lower activation energy. Transition metals are ideal catalysts because they have variable oxidation state and they can absorb reactants on their surface if they are in the solid form, and they can form complex ions with reactants in solution. There are two types of catalyst. The first one is called the heterogeneous catalyst. A heterogeneous catalyst is the catalyst that has a different phase than the reactant, meaning, or typically, it's when the catalyst is in a solid phase, while the reactants are either gaseous or they can be in solution. So how does it work as a heterogeneous catalyst or as a solid catalyst with a different phase of the reactant? There are three stages here for heterogeneous catalyst. The first one is the adsorption state. So the adsorption, the reactant molecule will bind to certain active sites on the metal surface. And then the reaction. So now the molecules of the reactants, which had adsorbed on the surface of the catalyst, their bonds will be weakened and they can form new bonds to form the products. Once the products have been formed, the third stage takes place, which is the desorption, where the products leave the surface, freeing up the active sites. Some examples that you need to know from your specification are the use of the iron as a catalyst, which is a solid catalyst, in the Haber process, where the Haber process is a reaction between nitrogen and hydrogen to form ammonia. All of these are gaseous. So the catalyst here is iron. And also the contact process, which is the reaction between sulfur dioxide and oxygen to give sulfur trioxide. Well, vanadium 5 oxide is used in sulfuric acid manufacture. So we need the sulfur trioxide to dissolve it in water to give the sulfuric acid. Also, we have the hydrogenation of alkenes where we use nickel here, and that converts the carbon-carbon double bond into carbon-carbon single bond. Catalyst poisoning, we can see the catalyst poisoning in case of heterogeneous catalyst, where sometimes if we have some impurities in the reactants, they can actually bind to the active sites on the surface of the catalyst, and they will prevent the contact between or adsorption of the reactants on the surface of the catalyst. So this will reduce the catalyst efficiency and can stop the reaction. Example of that is in the Haber process. So sulfur, there will be sulfur impurities in the hydrogen gas. We also have the homogeneous catalysis at the second time, where this is when the catalyst is in the same phase as the reactant. So usually they are all in solution. So this process involves three different steps. The first one is when the catalyst form an intermediate species with one of the reactants, and then this intermediate will react with the other reactant to give the final product, and the catalyst is regenerated at the end. Two examples that you need to know in your specification. The first one is the use of iron 2 plus as a catalyst in the reaction between peroxide disulfate with the iodide. In this case, the peroxide disulfate and the iodide, they both have negative charge, they repel each other. So the activation energy for the reaction is very high, the reaction is very slow. The presence of the iron 2 plus and the ability to have two different oxidation states and that it can be oxidized into iron 3 plus, it will play a role in this reaction as a catalyst. So first it can collide with the peroxide sulfate and it will form a redox reaction. So peroxide sulfate, this one, with the iron 2 plus, that will give you the iron 3 plus. So the iron will be oxidized while the peroxide sulfate will be reduced to give 2 of the sulfate ion. And then the iron 3 plus that is produced will now react with the iodide. So this is the intermediate that reacts with the iodide in the second step to give iodine, and then the catalyst is regenerated, which is the iron 2 plus. I didn't actually balance these equations, but you need to balance them in your exam. And this is the overall reaction for the process. And we also have the autocatalysis, where we use the manganese 2 plus as a catalyst, as a product in the reaction and as a catalyst to for the redox reaction between ethane diuate and manganate to give carbon dioxide and manganese. So the reaction simply is that it starts with the manganate reacting with manganese 2 plus. So we have the manganate, MnO4. Also, I'm not gonna balance it now, MnO4, reacting with the manganese 2 plus, that will give the manganese 3 plus. And this is then we have this is an intermediate which is going to the manganese 3 plus, react now with the C2O4 2 minus to give the manganese 2 plus and also the carbon dioxide. So manganese 2 plus here is formed as one of the products in the reaction, and it uses the manganese that is generated will actually be autocatalyzed or become an autocatalyst because it catalyzes the reduction of the manganese. Metal equiions are complex ions formed when a metal ion is surrounded by water ligands. Something can you have something like iron 3 plus surrounded by 6 molecules of water, or the copper 2 plus surrounded by 6 molecules of water. The water molecules will form coordinate bond with the metal ions. So what are the properties of these metal ions? First of all, these metal ions are slightly acidic, and the acidity comes from the ability of these metal ions or the equiions to donate the protons from the water molecules from the ligand to the solution when they are dissolved in water to form three H3 plus H3O plus ions. So we have 3 plus metal ions and we have the 2 plus metal ions. The 3 plus metal ions are more acidic than the 2 plus metal ions. We are talking about the aqua ions here. And the reason why is because of the higher charge density for the 3 plus metal ions. So they polarize the OH bond in the water ligands or in the water molecules, and then weaken the bond between the oxygen and hydrogen, and they can donate the proton. So they can lose the proton more easily. easily. Example of that, you can have the iron 3 plus aqua ion with 6 molecules of water. When you dissolve it in water, then it will start to donate one proton after the other to from three up to three different molecules from the water ligands to the water into the solution to give you this complex. This is the first one, and then it can have the second one with two hydroxides for water, where it donates two protons and then up to three protons. So the solution of the aqua ions of metal 3 plus ions are aqua ions are more acidic than the 2 plus. So what are the reactions of these aqua ions with different reagents? First of all, a reaction with hydroxide, it will undergo neutralization reaction because hydroxides are basic and the aqua ions are acidic. So when we have a small amount of the hydroxide ion, then these aqua ions, metal aqua ions, will act as an acid and they will donate the proton to the hydroxide, and then they're gonna form the insoluble, the hydroxides. So these insoluble hydroxides will have different colors depending on the aqua ion itself. And then in case of the 2 plus ions, or this is for both 2 plus or 3 plus ions, and it will do the same. So the 2 plus ions will donate two protons from two different molecules of water and will give you the hydroxide. You can either write the hydroxide like this, or you can write it as two of the water as a complex ion and four of the two of the hydroxide and four of the ammonium hydroxide. Is amphoteric hydroxide, meaning it acts as an acid in presence of a base and act as a base in presence of an acid. So when you have aluminum hydroxide, which is a solid, it's insoluble, in presence of an excess of the hydroxide ion, it will give you this complex ion, which is soluble. So aluminum was four of the OH minus. So it will donate an extra proton to the hydroxide to give you the water molecule. In presence of an acid like H3O plus or simply as hydrogen plus, it will act now as an base, and it will take three protons from the acid, and it will form the aqua ion of the aluminium with 6 molecules of the water instead of having three hydroxide ions. So it will take three protons, add each of these to one of the hydroxide ion to form in total 6 molecules of water ligands surrounding the aluminium ion. And this is, of course, soluble. So when you start with the aluminum hydroxide, which is a solid, with a base, excess base, or with an acid, in both cases, you will find that the soluble or the precipitate will dissolve. In case of ammonia, ammonia can act either as a base with the metal aqua ions, or sometimes it can act as a ligand. This is in presence of excess and specifically for copper. So as a base, it will act simply like hydroxide ion. So now what is going to happen is that the complex ion, the complex aqua ion, react with the ammonia, will react as an acid, donate the protons to the ammonia to give the ammonium ion, and then form the insoluble hydroxide, which is going to be colored or maybe white if it's aluminium. In case of the transition metals, it's going to be colored complexes. In case of presence of ammonia as in excess, it will act as a ligand in case of the copper. So when you have a copper hydroxide, which was formed when you don't have excess, when you added ammonia dropwise, it's formed first, and then you have excess of the ammonia added, then there will be a new complex ion formed between the ammonia and water molecule. So it's going to substitute these hydroxides, and it will give you the copper with four of the ammonia, two of the water molecule, and this is going to be a deep blue solution. So the precipitate, when you add excess of the ammonia, will turn into a deep blue solution. reaction of the metal equiines with the carbonate, we have two cases. The metal, which are 2 plus ions. So the 2 plus ions, equiines, when they react with the carbonate, they will give you the metal carbonate, which is going to be a precipitate. And in case of the 3 plus ions, because they are more acidic, so instead of making carbonate, the extra acid will react with the carbonate to give carbon dioxide and water. At the same time, what's going to be formed is the hydroxide. It's not going to form the carbonate, but will give you the hydroxide. So if you have the equiion of iron 3 plus ion and reacted with a carbonate, that will give you the hydroxides of the iron, and you can write it as FeOH3 and then H2O3, and this is going to be a precipitate, and this is in addition to the carbon dioxide and the water. In case of iron 2 plus, it will give you the iron carbonate. So this is with the iron 2 plus, it will give you iron carbonate, which both of these will be colored precipitate. So let's see the total of a summary of all of these reactions and these tests and what are the expected product or the expected observation. So if we have a testing with a hydroxide or ammonia dropwise, then with iron 2 plus, that will give us a green precipitate. The green precipitate would be the hydroxide of the iron 2 plus. And if you add excess of the hydroxide, there will be no change. So that will stay as a green precipitate. If you have excess of the ammonia, so after you add dropwise of the ammonia and give you a green precipitate, with the iron 2 plus, there will be no visible change as well because the green precipitate will stay, which is the hydroxide. So the ammonia here with the iron will only act as a base. With the carbonate, there will be also a green precipitate, but the green precipitate now is due to the formation of the iron carbonate, not due to the iron hydroxide. With iron 3, so hydroxide or ammonia, that will give you brown precipitate of the hydroxides. If you add excess of the hydroxide, there will be no change. That is going to stay, so it's not amphoteric here. So it's going to stay as the hydroxide of the iron 3, so brown precipitate. Also in excess of the ammonia will act just as a base, not to substitute the ligand. So you're still going to have the brown precipitate. And finally, with the carbonate, instead of having the iron carbonate, iron 3 carbonate, you're going to have the iron hydroxide and carbon dioxide gas. Copper 2 plus, this is a 2 plus ion. So with excess, with dropwise of the hydroxide or ammonia, it will form the hydroxides of the copper, and the hydroxide of the copper is blue, a precipitate. If you add excess of the hydroxide, there will be no change. You're still going to see the blue precipitate. But if you add excess of the ammonia, remember the ammonia will act as a ligand now to substitute the water molecules and will form this complex ion with 4 of the ammonia, 2 of the water, and the precipitate will dissolve and the solution will turn into deep blue. And finally, with the carbonate, it will give you the copper carbonate, which is blue-green precipitate. Finally, aluminum equiion, the aluminum equiion with hydroxide or ammonia, that will give you white precipitate of aluminum hydroxide. And if you add excess of the hydroxide, remember aluminum hydroxide that has been formed when you started to add the hydroxide will have an amphoteric property, so it will act as an acid. So the precipitate will dissolve to give you a colorless solution. So the colorless solution is due to the formation of the aluminum with OH minus 4 and 4. And then in case of excess of the ammonia, there will be no change. It will stay as a white precipitate of the aluminum hydroxide. And finally, with the carbonate, it will give you white precipitate of aluminum hydroxide, similarly like iron 3 plus, and also carbon dioxide gas. So